Subscribe to the channel and like the video. What if there's something out there even scarier than a black hole? This single question is enough to stir curiosity, spark fear, and open a door into the deepest mysteries of our universe. Black holes are already regarded as the ultimate cosmic monsters, the final word in destructive astrophysics. They warp time, tear apart stars, and consume anything that dares to cross their invisible boundaries. And yet, what if black holes are not the end of the story? What if they are not the most terrifying thing the universe has in its arsenal? Imagine something that looks like a black hole, acts like a black hole, but harbors a secret inside so strange that it could completely rewrite our understanding of physics. This is not a science fiction plot, it is a real scientific speculation. The idea is that there may exist a type of star so bizarre, so unnerving, that even black holes pale in comparison. These are known as gravastars, or gravitational vacuum stars. Now, let's take a step back. Before we plunge into the heart of gravastars, let's revisit why black holes are considered terrifying in the first place. Think about what they represent: regions in space where gravity becomes so extreme that nothing, not even light, can escape. Once you cross the event horizon, you are doomed, no matter who you are, what you are, or how fast you're moving. There is no negotiation, no escape route, no technology that could save you. And inside, at least according to Einstein's general relativity, lies the singularity, a point where density becomes infinite, where the known laws of physics break down, and where reality itself seems to shatter into nonsense. It's almost as if nature places a do not enter sign at the boundary. And yet, we are drawn to these objects like moths to flame because they symbolize the absolute extremes of what is possible in our universe. But here comes the twist. What if what we thought were black holes aren't black holes at all? What if they are imposters, camouflaged in the darkness of space, mimicking all the outward signs of a black hole, while inside, something far stranger is at play? This is the hook of the gravastar hypothesis. If black holes are terrifying because of their absolute finality, gravastars are terrifying because of their ambiguity. They pretend to be one thing but are, in reality, something far more exotic, something that could one day reveal itself in explosive and catastrophic ways. So when I ask, what if there's something out there even scarier than a black hole? I'm really asking, what if our deepest fears about the cosmos are actually incomplete? What if the universe is hiding secrets that not only challenge science but shake the very foundations of how we imagine space, time, and energy? Gravastars are a reminder that the universe may still have surprises in store, surprises that could make the already frightening concept of black holes look tame in comparison. When we step into the mysterious world of gravastars, we are essentially walking into one of the strangest what-ifs in modern astrophysics. Gravastars, short for gravitational vacuum stars, are not science fiction inventions but rather serious theoretical constructs proposed by physicists who dared to ask whether black holes are the final word in cosmic collapse. The mystery of gravastars lies in the fact that they are both familiar and alien at the same time. From the outside, they could appear almost indistinguishable from black holes. They would bend light, warp space-time, and even emit the same type of gravitational signals we associate with collapsing stars. To an observer millions of light-years away, staring at one with even the most advanced telescope, it would look and act like a black hole. But deep inside, according to this hypothesis, something entirely different is happening. So, what exactly are gravastars? At their core, gravastars are theorized to be exotic, ultra-compact objects that form in place of black holes. Instead of collapsing into an infinitely dense singularity wrapped in an event horizon, a dying star could, under certain conditions, stabilize into a gravastar. That means, instead of being swallowed into oblivion at a singular point, matter could be halted at the brink of collapse, giving rise to a very different type of object. This makes gravastars both fascinating and frightening, because they suggest that the ultimate fate of massive stars may not always be a black hole. Why would scientists even consider such a bizarre alternative? The main reason is that black holes, as elegant as they sound in equations, come with deep paradoxes. The most infamous of these is the information paradox. If black holes truly swallow everything, including information about particles, then that information is gone forever. But according to quantum mechanics, information cannot be destroyed. This clash between relativity and quantum mechanics is one of the biggest unresolved problems in physics. Gravastars present themselves as a possible solution. By removing the singularity and replacing it with a strange vacuum-like core, gravastars may preserve information in ways black holes cannot. Another reason gravastars have attracted attention is that they offer a more stable alternative. Think of it like this: black holes represent a breakdown of the rules. A singularity is a cosmic contradiction, a place where we are forced to admit that our laws of physics no longer make sense. Gravastars, on the other hand, propose that nature may have found a workaround. Instead of letting matter collapse into infinity, perhaps the universe cleverly stabilizes it into a different structure, one that avoids paradoxes and infinities altogether. And yet, the mystery lingers because we don't know whether gravastars truly exist. They are, at this point, purely theoretical. No telescope has ever spotted one with absolute certainty. No gravitational wave observatory has confirmed their signature. But their theoretical possibility is tantalizing enough that physicists continue to explore them as potential imposters hiding in plain sight among the black holes we've already catalogued. This duality, being nearly indistinguishable from black holes, while possibly being something radically different, makes gravastars incredibly mysterious. They challenge us to rethink what we think we know about the darkest, most terrifying objects in the cosmos. They leave us wondering, when we peer into the abyss and call it a black hole, are we actually looking at something far stranger? Black holes have held humanity's imagination hostage for decades, not just because they are mysterious, but because they represent the very extremes of nature. They are objects where the ordinary rules of reality no longer apply, where space and time themselves bend into shapes our minds can barely comprehend. To understand why gravastars are seen as terrifying alternatives, we first need to revisit what makes black holes so frightening in the first place. Only by grasping the nature of these cosmic monsters can we appreciate why an alternative like the gravastar could be even more unnerving. At the heart of black holes lies a concept that unsettles even the most seasoned physicists: the singularity. According to Einstein's theory of general relativity, if a massive star collapses under its own gravity, it can reach a point of no return where matter is compressed into an infinitely small, infinitely dense point. That's the singularity. Imagine billions of tons of matter, entire stars, galaxies worth of mass, all compacted into something with no physical size, no volume, and yet holding tremendous mass. The equations of relativity predict it, but our minds cannot fully wrap around it. In the singularity, the density becomes infinite, and the laws of physics, laws that govern everything from falling apples to the dance of galaxies, simply stop working. It's as if nature itself hits a glitch, a breakdown where the universe refuses to show us what lies beneath the veil. But the singularity doesn't just sit out in the open. It is shielded by a boundary known as the event horizon. This is the ultimate cosmic border, the invisible point of no return surrounding a black hole. Cross it, and escape becomes impossible. Even light, the fastest thing in the universe, cannot break free once it crosses that threshold. This is why black holes appear black. They are not glowing stars or radiant planets, but instead, gaping mouths of darkness, swallowing everything that strays too close. To an outside observer, anything falling into a black hole seems to slow down, stretching and dimming as it approaches the event horizon, never quite crossing it. Yet from the perspective of the falling object itself, the journey is swift and final, an unstoppable plunge into oblivion. Now, one of the most viscerally terrifying aspects of black holes is the process nicknamed spaghettification. This occurs because gravity near a black hole is not uniform. It changes drastically over very short distances. If you were unfortunate enough to fall feet first toward a black hole, the gravitational pull on your feet would be immensely stronger than the pull on your head. The difference in force would stretch you, elongating your body like a strand of spaghetti. Your very atoms, molecules, and eventually subatomic particles would be ripped apart by this tidal stretching. In the realm of black holes, death isn't simply destruction. It is a distortion so complete that your existence is unraveled down to the tiniest scales. Adding to this cosmic horror is the warping of time itself near black holes. Time, which we normally think of as constant and steady, begins to behave in bizarre ways under intense gravity. To an outside observer, someone falling toward a black hole appears to slow down, their movement stretching into eternity, frozen at the edge of the event horizon. But for the falling individual, time proceeds normally until they cross into the abyss. This divergence between perspectives illustrates just how alien black holes truly are. They don't just destroy matter, they fracture reality, creating contradictions in how events unfold depending on where you stand in relation to them. Let's not forget the scale of black holes either. While small ones can be formed by collapsing stars, supermassive black holes exist at the centers of galaxies, with masses millions or even billions of times greater than our Sun Sagittarius A*. The black hole at the heart of the Milky Way is about 4 million solar masses. In other galaxies, we've found giants tens of billions of times the Sun's mass. These entities sit at the cores of galaxies, orchestrating the dance of stars around them, like monstrous anchors holding entire cosmic cities in their grip. The sheer size and power of these objects are enough to evoke awe, terror, and fascination all at once. And then there's the information paradox tied to black holes. According to the principles of quantum mechanics, information about the state of matter cannot be destroyed. But when matter falls into a black hole, it seems that all details about it, the structure, the composition, the quantum data, are lost forever beyond the event horizon. Hawking radiation, the faint emission predicted by Stephen Hawking, suggests that black holes could eventually evaporate. But if they disappear, what happens to the information they swallowed? Does it vanish with them? That possibility contradicts the fundamental rules of physics, leaving us with an unsolved puzzle that gnaws at the foundations of science. All of this combined, the singularity, the event horizon, the spaghettification, the time distortion, the paradox of lost information, makes black holes not only terrifying but deeply mysterious. They are natural laboratories at the edges of reality, places where our theories collapse, and where the cosmos seems to hide its darkest secrets. And here's where the comparison with gravastars begins to take on its chilling weight. Black holes are frightening because they are absolute, inevitable, final. They consume and crush without hesitation. Yet, gravastars whisper a different kind of terror, the terror of uncertainty, of cosmic imposters masquerading as black holes while harboring something far stranger inside. Black holes frighten us because they are ultimate destroyers. Gravastars frighten us because they suggest that even what we think we know about these destroyers could be wrong, that behind the curtain of cosmic darkness, the universe may be hiding truths even stranger than our worst nightmares. When we speak about gravastars, or gravitational vacuum stars, we are stepping into a realm where science begins to blur with imagination, yet remains rooted in rigorous mathematics and theoretical physics. The gravastar concept wasn't dreamed up in a science fiction novel. It was born out of serious attempts to tackle one of the greatest unsolved puzzles in modern physics, the paradoxes created by black holes. To fully appreciate why gravastars were proposed, we must remember that black holes, as elegant and terrifying as they are, come with baggage. They predict singularities, those infinitely dense points where our equations break down, and they carry the infamous information paradox, which seems to break the laws of quantum mechanics. For decades, scientists have wrestled with this uncomfortable contradiction. On one hand, general relativity predicts black holes. On the other, quantum theory insists that information cannot be destroyed. These two pillars of physics clash violently at the heart of black holes. Gravastars step into the story as a proposed solution to this clash. The gravastar idea essentially asks, what if nature avoids creating singularities altogether? Instead of letting matter collapse into infinity, what if the universe stabilizes it in some new, exotic form? Gravastars are the answer to that what if. They are hypothetical objects that look almost exactly like black holes from the outside but are fundamentally different on the inside. Their defining feature is that they replace the black hole's singularity and event horizon with something else, a vacuum-like core filled with energy, wrapped in a thin shell of ultra-dense matter. The term gravitational vacuum star is not just a catchy name, it literally describes what these objects might be. At their heart is a kind of vacuum energy, similar to the mysterious dark energy thought to drive the expansion of the universe. Instead of collapsing into infinite density, the core of a gravastar could be a region dominated by this vacuum energy, exerting an outward pressure that counteracts the inward pull of gravity. Around this core would exist a thin, ultra-dense shell that balances the two forces, gravity pulling in, vacuum energy pushing out. This delicate balance prevents the formation of a singularity, sidestepping one of the biggest problems of black holes. So why is this concept so radical and intriguing? Because it suggests that the universe may have a built-in safety mechanism. Where black holes represent the glitch in physics, the point where everything we know fails, gravastars propose that perhaps the universe never lets it get that far. Maybe singularities don't exist at all. Maybe what we've been calling black holes are really gravastars in disguise, and we've been misinterpreting their true nature all along. This theoretical idea offers an elegant way to resolve paradoxes. For instance, in gravastars, there is no singularity to destroy information. The information paradox might be avoided because matter doesn't vanish into infinity. It interacts with the strange vacuum core or the shell in ways that could, in theory, preserve the information, even if in forms we don't yet understand. That makes gravastars not only fascinating but potentially essential to reconciling relativity and quantum mechanics. And yet, here lies the truly chilling aspect. Gravastars would be almost indistinguishable from black holes to any observer at a distance. Their gravity would bend light, their presence would warp spacetime, and their behavior would mimic black holes so closely that astronomers might not be able to tell them apart. Imagine the implication. Many of the black holes we've discovered and catalogued could actually be gravastars. They could be sitting silently at the centers of galaxies, including our own Milky Way, pretending to be black holes while holding something entirely different within. This duality, the fact that gravastars are designed to solve paradoxes but may, in doing so, represent something more alien than we've ever imagined, makes them such a compelling idea. They're not just an academic curiosity. They are a profound possibility that forces us to question everything we think we know about cosmic death, collapse, and the ultimate fate of matter. So in introducing gravastars, we're not just describing another type of star. We're exploring a radical alternative to one of the most established concepts in modern astronomy. We're asking, what if the terrifying black holes we fear are only shadows, disguises for something even stranger? What if the abyss is not what we think it is? Gravastars hold the possibility that the universe, in its infinite complexity, has one more surprise waiting for us, hidden in plain sight. The origin of the gravastar concept takes us back to the early 2000s, when two physicists, Paolo Mesa and Emil Mottola, introduced a bold new idea that would ripple through the astrophysics community. In 2001, they published a paper that dared to challenge the traditional picture of black holes. While black holes had long been accepted as the inevitable outcome of stellar collapse, Mesa and Mottola asked, what if we've misunderstood the very endgame of gravitational collapse? Paolo Mesa, a Polish-born theoretical physicist, had already been exploring ideas related to quantum gravity and exotic states of matter. Emil Mottola, an American physicist working at Los Alamos National Laboratory, was deeply interested in fundamental questions about vacuum energy and cosmology. Together, they sought a way to reconcile the inconsistencies between Einstein's general relativity and the principles of quantum mechanics. Their collaboration gave birth to the gravastar model, or what they officially called the gravitational vacuum condensate star. Their motivation stemmed from the paradoxes that black holes introduced into physics. As I mentioned earlier, black holes predict singularities, points where the density of matter becomes infinite and where time and space collapse into a one-dimensional nothingness. General relativity confidently predicts these singularities, but quantum mechanics recoils in horror, because infinities are not supposed to exist in physical reality. Furthermore, the information paradox, the idea that information about matter falling into a black hole could be lost forever, represented another clash. To Mesa and Mottola, this meant that perhaps the traditional picture of black holes wasn't the whole truth. So they proposed an alternative. Instead of allowing a star to collapse fully into a black hole, what if the collapse halted just before reaching that catastrophic singularity stage? What if, instead of forming an event horizon that swallows everything, the collapsing matter transformed into a new, exotic state, stabilized by vacuum energy? This is where their idea of the gravastar came from. The structure they described was elegant, almost poetic in its simplicity. At the very center would be a region filled with vacuum energy, a kind of repulsive force similar to the mysterious dark energy thought to drive the accelerated expansion of the universe. Surrounding this core would be a thin, ultra-dense shell of matter, acting as a buffer between the vacuum core and the outside universe. Finally, beyond the shell, space-time would look almost identical to that around a black hole, making the gravastar effectively indistinguishable from one to distant observers. The brilliance of Mesa and Mottola's idea was that it eliminated the singularity altogether. No infinities, no breakdown of physical laws, no violation of quantum mechanics. The event horizon, too, was reimagined. Instead of an absolute point of no return, gravastars might possess a quasi-horizon, where light and matter could be trapped for long periods without being truly lost. In this way, the gravastar offered an escape from the paradoxes that black holes forced upon science. When Mazur and Mottola first proposed their theory, it was met with both fascination and skepticism. On the one hand, physicists admired the creativity of the solution. Here was a model that seemed to neatly sidestep some of the most troubling aspects of black hole physics. On the other hand, many were hesitant. Gravastars were, and still are, entirely hypothetical. No direct observational evidence supports their existence. Black holes, by contrast, are strongly supported by decades of astronomical data. The motion of stars orbiting invisible masses, gravitational wave detections from black hole mergers, and even the historic first image of a black hole's shadow captured by the Event Horizon Telescope in 2019. Nevertheless, Mazur and Mottola's 2001 paper planted a seed in the scientific imagination. It opened the door for alternative models of compact objects, spurring new research into what might lie beyond the veil of collapsed stars. Other scientists began to explore variations of the gravastar concept, considering how they might form, how stable they would be, and how we might distinguish them from black holes using gravitational waves or high-energy emissions. It's worth noting how radical their proposal truly was. At a time when black holes were becoming almost universally accepted as real astrophysical entities, Mazur and Mottola were effectively saying, maybe what we've been calling black holes are not black holes at all. It was a challenge to orthodoxy, a reminder that in science, even the most seemingly secure ideas are open to questioning. Today, as we push the limits of observation with gravitational wave detectors like LIGO and Virgo, and with next-generation telescopes, the possibility of testing whether some black holes are actually gravastars doesn't feel as far-fetched as it once did. Mazur and Mottola's work continues to serve as a reminder that the universe might be stranger than we dare imagine, and that sometimes the boldest ideas are the ones that survive the longest in the halls of theoretical physics. So when we talk about gravastars today, we owe it to the visionary work of these two physicists in 2001. Their willingness to question the inevitability of black holes gave us a new lens through which to view the cosmos, one where even the darkest, most terrifying entities might conceal a secret we have yet to uncover. When comparing black holes to gravastars, the core difference, quite literally, lies at their very centers. In the case of a black hole, the core is thought to be a singularity, a point of infinite density where matter collapses into an infinitely small region and spacetime itself breaks down. This is perhaps the most unsettling aspect of black holes, because singularities are not just physically destructive, they are mathematically nonsensical. The laws of physics that govern everything else in the universe, motion, energy, even the flow of time, cease to function in the way we understand them. But gravastars, if they exist, rewrite this story. Instead of a singularity lurking at their heart, gravastars may contain something far stranger, a vacuum-like energy core. This is not empty space in the usual sense. To understand it, we need to think about what physicists mean by vacuum energy. In quantum field theory, the vacuum isn't truly empty. Even the emptiest space imaginable seethes with activity. Virtual particles flicker in and out of existence, energy fluctuates, and space itself carries a kind of background energy. This energy, when spread throughout the universe, is believed to be linked to dark energy, the mysterious force driving the accelerated expansion of the cosmos. Now imagine compressing that concept into the heart of a collapsing star. Instead of collapsing forever into a singularity, the star might undergo a kind of phase transition, like water freezing into ice, and transform into a region dominated by vacuum energy. This vacuum-like energy core would exert an outward pressure, similar to how dark energy pushes galaxies apart on cosmic scales. In the case of a gravastar, this outward push balances the immense inward pull of gravity from the star's mass. The result is a bizarre equilibrium. Gravity tries to squeeze everything down, but the vacuum energy pushes back, preventing collapse into a singularity. This difference changes everything. A black hole singularity is a dead end, a breakdown in understanding. A gravastar's vacuum core, by contrast, is a possible escape hatch from that dead end. Instead of infinite density and destruction, you get a region filled with strange energy that may store information or even maintain stability in ways black holes cannot. To visualize it, imagine two scenarios. 1. Black hole core. Matter collapses endlessly, becoming infinitely dense, until it vanishes into a singularity hidden behind an event horizon. Inside, nothing can survive. Not even physics survives. 2. Gravastar core. The collapse halts just short of singularity formation. Instead of infinite density, you get a bubble of vacuum energy at the center, surrounded by an ultra-thin but ultra-dense shell of matter. The laws of physics, instead of breaking down, shift into a new mode of operation. Strange, yes, but not nonsensical. This fundamental difference also influences the external behavior of the object. From far away, a gravastar may look nearly identical to a black hole. Its gravitational field would bend light the same way, and its immense mass would tug at nearby stars with the same invisible hand. But up close, the difference could be profound. A gravastar might lack a true event horizon, meaning that while light and matter could get trapped near its surface for long stretches of time, they wouldn't necessarily vanish forever. In theory, information could still be preserved, solving the infamous information paradox. The idea of a vacuum-like energy core also introduces new possibilities for physics. It suggests that the ultimate fate of collapsing stars may not be destruction into infinity, but transformation into exotic new states of matter and energy. It implies that nature abhors singularities, preferring instead to stabilize collapse with mechanisms we don't yet fully understand. And it forces us to reckon with the possibility that what we've been calling black holes might, in some cases, be these strange imposters with vacuum hearts. But here's where the fear comes in. If gravastars really do have vacuum-like energy cores, they might be capable of storing unimaginable amounts of energy, locked away in their centers like ticking cosmic bombs. If the balance between gravity and vacuum energy were ever disrupted, if the shell surrounding the core were to fail, the stored energy could, in theory, be unleashed in a catastrophic explosion. Black holes, for all their destructive power, are at least stable in their finality. Gravastars, by contrast, may be dangerous precisely because they are not final. They are balanced, precarious, and potentially unstable. So while the singularity at the heart of a black hole terrifies us because it's an abyss where physics dies, the vacuum-like core of a gravastar terrifies us because it's a mystery wrapped in potential energy. It's not the end of the story, it's a strange new beginning, with consequences we can't yet predict. This core difference is what makes gravastars such a fascinating and unsettling alternative. Black holes are monsters of inevitability. Gravastars are monsters of uncertainty. One represents the ultimate collapse. The other represents the possibility that collapse doesn't end where we thought it did, that it transforms into something even stranger. And sometimes, uncertainty is far scarier than inevitability. The gravastar structure is one of its most fascinating and eerie qualities because it is unlike any ordinary star, planet, or even a black hole. It is composed of 3 distinct regions that together create a bizarre balance of forces, allowing it to mimic the behavior of a black hole while hiding something profoundly different within. This layered structure is what sets gravastars apart, and understanding it is crucial to grasping why they might exist, how they might function, and why they are so terrifying to contemplate. At its heart lies the vacuum core, a region filled not with ordinary matter but with what physicists call vacuum energy. This is the innermost layer, and it is radically unlike the dense singularity predicted in black holes. Instead of infinite density and collapsing matter, the vacuum core is thought to contain something akin to dark energy, a repulsive force that pushes outward. In the larger universe, dark energy is believed to drive the accelerating expansion of galaxies, keeping the cosmos ever stretching. In a gravastar, this same type of energy is trapped inside, creating a bubble at the center that resists being crushed further by gravity. The vacuum core is not simply empty space. It is a false vacuum, a state where space itself holds energy, like a compressed spring straining against being squeezed. This makes the core an incredibly strange and potentially unstable reservoir of power, quietly balancing against collapse. Surrounding this eerie core is the thin ultra-dense shell of matter. This is perhaps the most critical part of the gravastar's structure because it acts as the barrier between the vacuum energy inside and the universe outside. Think of it as a cosmic pressure cooker lid, holding in the outward push of the vacuum core while simultaneously containing the inward crushing force of gravity. Without this delicate balance, the gravastar could not exist. The shell is theorized to be unimaginably dense, far denser than neutron star matter, which already packs a sun's worth of mass into a sphere only about 20 kilometers wide. This thin layer must be strong enough to withstand the constant tug-of-war between gravity trying to collapse it and vacuum energy trying to explode it outward. It's a razor's edge of stability, an equilibrium that makes the very existence of gravastars precarious and unsettling. Finally, beyond this shell, we arrive at the outside region of spacetime, which, at least mathematically, looks almost identical to the spacetime around a black hole. This is part of the reason gravastars are so hard to distinguish from their darker cousins. From far away, an astronomer observing the bending of light, the orbits of nearby stars, or even the gravitational waves emitted by mergers would see almost the same signals as those predicted by a black hole. The external geometry of spacetime around a gravastar is nearly indistinguishable from that of a Schwarzschild black hole. This means that gravastars can sit in the universe masquerading as black holes, hidden in plain sight. Only when you probe close to the supposed event horizon would the differences become apparent, and even then, the differences may be subtle, perhaps manifesting as faint echoes in gravitational wave signals or unusual radiation patterns. To recap this three-layered structure: 1. Vacuum core, a bubble filled with vacuum energy or dark energy, exerting outward pressure. It prevents collapse into a singularity and stores an enormous amount of energy. 2. Thin ultradense shell, a razor-thin boundary of matter that stabilizes the system by balancing gravity's inward pull against the vacuum's outward push. This shell is what keeps the gravastar intact and prevents it from exploding or collapsing. 3. Outside region of spacetime. Externally, the gravastar warps space and time in a way almost indistinguishable from a black hole, making it extraordinarily difficult to detect or confirm observationally. This layered arrangement is what makes gravastars so unnerving. They are not simply exotic stars, they are cosmic imposters that mimic black holes while hiding an alien-like architecture inside. The vacuum core is strange enough, but the thin shell raises additional questions. What kind of matter could withstand such forces? How could such a structure form naturally during the death throes of a star? And if it did form, how long could it remain stable? Some theories suggest gravastars might be stable for billions of years, long enough to exist in our universe today, while others argue they may eventually collapse or explode, releasing catastrophic bursts of energy. In a way, the gravastar's three layers represent three different faces of the universe. The vacuum core is the face of cosmic repulsion, echoing the dark energy that stretches galaxies apart. The thin shell is the face of extreme matter, denser than anything else we know of, like a fortress wall at the boundary of known physics. And the outer spacetime is the face of deception, projecting the appearance of a black hole while concealing a radically different reality. This structure not only challenges our understanding of stellar collapse but also redefines what we might consider possible in astrophysics. While black holes represent the ultimate collapse into nothingness, gravastars suggest that perhaps the cosmos prefers balance over destruction, even if that balance is precarious, alien, and terrifying. At the heart of a gravastar lies its most enigmatic and unsettling feature, the vacuum energy core. Unlike a black hole singularity, which represents the ultimate collapse of matter into an infinitesimal point, the gravastar center is theorized to be filled with a peculiar form of energy that physicists sometimes liken to dark energy. This is not energy in the conventional sense, heat, light, or kinetic energy, but a fundamental property of space itself. In the wider universe, dark energy is responsible for the accelerating expansion of galaxies, a mysterious force that pushes space apart at cosmic scales. Within a gravastar, this same type of energy is compressed into a confined region, creating an intense outward pressure that resists the star's gravitational collapse. This vacuum energy is sometimes described as a false vacuum, a state of space where energy density remains constant even in the absence of matter. It is a form of repulsion, in stark contrast to the attractive pull of gravity. Imagine compressing a balloon. As you squeeze, the air inside pushes back. Now replace the air with the fabric of spacetime itself, infused with energy that cannot escape, and you begin to get a sense of how the vacuum core works. It exerts a pressure that pushes outward against the relentless inward force of gravity. This balance is what allows a gravastar to maintain its structure, preventing the collapse into a singularity that would normally occur in a black hole. The vacuum energy at the core of a gravastar is not just a stabilizing mechanism. It is a reservoir of unimaginable potential. If the equilibrium were ever disturbed, if the outer shell were to crack or the distribution of vacuum energy shifted, it could release enormous amounts of energy, potentially rivaling the most energetic phenomena in the universe. The implications are staggering. A single gravastar could store energy sufficient to alter its surroundings dramatically, impacting nearby stars, planets, or even entire stellar systems. The concept of vacuum energy within gravastars also has profound implications for physics itself. In black holes, the singularity is a point where classical physics breaks down, and quantum effects are expected to dominate, but we have no complete theory to describe it. In a gravastar, however, the core avoids the singularity entirely. Instead, the laws of physics remain intact, though they operate in an extreme, exotic state of matter and energy that we have never observed directly. This allows physicists to model the behavior of gravastars in a way that is consistent with both general relativity and quantum mechanics, offering a potential bridge between the two domains, a long-sought goal in theoretical physics. The outward push of vacuum energy also has consequences for how gravastars might interact with light and matter. While black holes trap everything that crosses the event horizon, a gravastar's quasi-horizon could allow light and radiation to linger near its surface for extended periods before eventually escaping. This means that, unlike black holes, gravastars might preserve information about what falls into them. It's a subtle distinction, but it addresses one of the most troubling paradoxes in modern physics, the information paradox. If gravastars exist, they could store or release information in ways that black holes cannot, challenging our understanding of entropy, causality, and the ultimate fate of matter in the cosmos. From a cosmic perspective, the presence of vacuum energy makes gravastars almost like tiny, self-contained universes. They are objects where the familiar rules of matter, energy, and gravity coexist in a delicate balance, yet on the edge of potential catastrophe. The thin shell surrounding the vacuum core is critical because it confines this energy and maintains equilibrium. Without it, the outward pressure could overcome gravitational pull, leading to an explosive release of energy, a scenario that could manifest as a sudden, violent outburst detectable across galaxies. This combination of stability and potential volatility is what makes the vacuum energy at the core of gravastars so fascinating and terrifying. It is a form of energy that we cannot directly observe, yet its effects could dominate the fate of the gravastar and its surroundings. The notion that the center of a star could be filled with this exotic energy, quietly pushing outward, adds a layer of unpredictability to objects that might otherwise appear to be inert or dormant. The idea of vacuum energy also links gravastars to broader cosmological questions. Dark energy remains one of the great mysteries of the universe. It is everywhere, yet invisible, influencing the expansion of the cosmos but eluding direct measurement. If gravastars truly exist, they might offer a laboratory for understanding how vacuum energy behaves under extreme conditions. Unlike the diffuse dark energy permeating empty space, the vacuum core of a gravastar concentrates it in a confined, dense environment, potentially amplifying its effects and offering clues to its fundamental properties. Ultimately, the vacuum energy at the core of a gravastar transforms it from a simple stellar remnant into a cosmic enigma. It is not merely a passive feature, it is an active player in the balance of forces that defines the object's existence. This energy simultaneously stabilizes the gravastar, prevents a catastrophic collapse, and stores potential energy of an almost incomprehensible magnitude. It is an invisible, omnipresent force pushing outward, a silent tension holding the structure together while keeping open the possibility of sudden, violent change. The thin, ultra-dense shell of a gravastar is perhaps its most delicate yet critical component. While the vacuum energy at the core pushes outward with immense force, the shell is the barrier that prevents that energy from simply blowing the object apart. Simultaneously, it bears the full brunt of gravity's inward pull, exerted by the gravastar's enormous mass. The shell is effectively the cosmic tightrope walker, maintaining an equilibrium that allows the gravastar to exist in a stable configuration, a feat that seems almost miraculous given the forces at play. Physically, the shell is theorized to be incredibly thin relative to the gravastar's overall size, yet it is composed of matter so dense that it surpasses anything we see in neutron stars. Neutron stars are already mind-bogglingly compact. A sugar cube-sized amount of their material would weigh billions of tons on Earth. The shell of a gravastar, though thinner, is thought to have a comparable, if not higher, density. This extreme density gives it the structural integrity required to contain the vacuum energy core, counteracting the outward push without collapsing under its own weight. From a mechanical perspective, the shell operates like a finely tuned tensioned membrane. Imagine a balloon filled with a powerful expanding gas, but the balloon's surface is made of the strongest material conceivable. The outward pressure of the gas is immense, but the integrity of the balloon's surface keeps the system intact. Similarly, the gravastar's shell maintains a delicate balance, ensuring that neither gravity nor vacuum energy dominates completely. If gravity were to slightly overwhelm the shell, the vacuum energy would be compressed, potentially destabilizing the system. If the vacuum energy were to slightly exceed the shell's capacity to contain it, an explosive release of energy could occur. This constant tug-of-war defines the very existence of the gravastar and makes it a remarkably precarious object. The shell also plays a crucial role in shaping the gravastar's interaction with the outside universe. From a distance, the gravastar appears almost identical to a black hole. Its shell contributes to the gravitational lensing effects, bending light in a way that mirrors the predictions for a black hole of the same mass. However, the presence of the shell and the vacuum energy beneath it changes how the gravastar might respond to infalling matter. Unlike black holes, which trap everything irretrievably past the event horizon, a gravastar's shell may allow for temporary storage or deflection of matter. Depending on the dynamics, matter might linger near the shell, interacting with the extreme conditions there, potentially radiating energy or being ejected in unusual ways. This is one of the reasons why gravastars could be misidentified as black holes. Their external gravitational influence is nearly identical, but the internal dynamics differ radically. The composition of the shell is another area of profound mystery. Theoretically, it must be a type of matter that is extraordinarily incompressible, yet capable of withstanding pressures far beyond what we can create in laboratories on Earth. Some models suggest exotic forms of degenerate matter, potentially composed of quark-gluon plasma or other states of matter that only appear at extremely high densities. In essence, the shell must act like a pressure valve, infinitely strong yet precisely calibrated to the outward force of the core. Any slight perturbation could lead to instability, making the gravastar a cosmic tightrope act, teetering on the edge between stability and collapse. This balance between the outward push of dark energy and the inward pull of gravity gives gravastars their most paradoxical property. They are both incredibly stable and incredibly dangerous. The shell contains energy that, if released suddenly, could rival the most violent events in the universe, including supernovae and gamma-ray bursts. This latent potential makes gravastars unpredictable. Even if we could locate one and measure its mass and radius, we might still have no reliable way of knowing how close it is to instability, or what would happen if the equilibrium were perturbed by external forces, such as the collision with another massive object. The shell also influences the gravastar's thermal and radiative properties. Unlike black holes, which are expected to radiate only Hawking radiation, gravastars may allow for limited emission of energy through subtle interactions at the shell. Photons or other particles could, in principle, be reflected, trapped temporarily, or even accelerated to high energies near the shell's boundary. This gives gravastars a potential observational signature, although distinguishing it from black hole behavior remains extremely challenging. The shell is, therefore, both protector and gatekeeper. It maintains structural integrity while mediating the gravastar's interactions with the cosmos. Ultimately, the shell is the linchpin of the gravastar's existence. Without it, the outward pressure of the vacuum energy would tear the object apart. With it, the gravastar achieves a delicate stability that allows it to persist over cosmic timescales. Yet, this balance is inherently precarious. The slightest perturbation, whether from an infalling star, gravitational waves from a nearby merger, or internal instabilities, could tip the system into catastrophic failure. This combination of resilience and latent danger is a hallmark of gravastars, making them both fascinating to theorists and terrifying to imagine. One of the most striking and profound differences between gravastars and black holes is their ability to avoid a singularity. In black holes, a singularity represents a point where the known laws of physics collapse along with the matter itself, where density becomes infinite and space-time curvature grows without bound. It is the ultimate expression of gravitational dominance, a region where matter is crushed into nothingness and our understanding of time, space, and energy breaks down entirely. Singularities are terrifying not only because of what they do to matter, but also because they are places where science reaches a limit. We can write equations describing their approach, but what actually happens inside is fundamentally unknowable. Gravastars, by contrast, are designed to circumvent this cosmic dead end. At their core is a vacuum-like energy region that resists collapse. Instead of matter being squeezed into an infinitely dense point, the vacuum energy exerts outward pressure that counterbalances gravity. This prevents the formation of a singularity entirely. The presence of this repulsive energy is not just a subtle tweak, it fundamentally changes the internal structure and evolution of the object. Where a black hole represents the triumph of gravitational compression, a gravastar is a delicate equilibrium of opposing forces, a cosmic stalemate that preserves space-time rather than destroying it. The key to avoiding a singularity lies in the interaction between the vacuum energy at the core and the ultradense shell surrounding it. In black holes, there is nothing to halt the inward collapse of matter once it passes the event horizon. All mass is inexorably drawn to the central singularity. In a gravastar, however, the outward pressure from the vacuum core meets the inward pull of gravity at the shell, creating a stable, albeit extremely dense, boundary. Matter is not crushed to infinite density. It is effectively contained. The result is a structure that, from the outside, can mimic a black hole perfectly, yet internally, it is free from the paradoxes that singularities pose. Avoiding a singularity has several implications for physics. For one, it maintains the integrity of known laws of physics, including general relativity, which would otherwise break down at a singularity. It also provides a potential solution to the so-called information paradox. In black holes, information about the matter that falls in appears to be lost forever, violating principles of quantum mechanics. If gravastars exist, however, the absence of a singularity means that information might be preserved or at least transformed in ways that are consistent with quantum rules. This makes them an appealing solution from a theoretical standpoint, as they reconcile aspects of relativity and quantum mechanics that are otherwise in tension. Moreover, the lack of a singularity also has fascinating implications for time and space within the gravastar. In a black hole, time effectively stops at the singularity, and the geometry of space-time becomes infinitely curved. Inside a gravastar, the vacuum core maintains a finite, well-defined space-time, albeit one subject to extreme conditions. This means that, in principle, the internal structure could support phenomena that are impossible within a singularity, such as exotic particle interactions or even forms of energy storage that do not exist anywhere else in the universe. While these ideas remain speculative, they illustrate the profound difference between a singularity-bound black hole and a singularity-free gravastar. Avoiding a singularity also has consequences for stability and potential catastrophic events. While black holes are generally stable once formed, essentially eternal prisons for matter, gravastars exist on a knife edge. The balance of forces must be maintained precisely. If the equilibrium between the outward push of the vacuum core and the inward pull of gravity is disrupted, the gravastar could either collapse, converting the vacuum energy into matter or radiation, or explode violently, releasing its stored energy in a manner that could rival the brightest cosmic explosions. This duality of potential outcomes makes gravastars simultaneously safer for the laws of physics internally yet more terrifying in terms of their energetic potential. In practical terms, the avoidance of a singularity could mean that gravastars are more than just exotic theoretical objects. They could be laboratories of extreme physics. Observing one, if we could, might allow us to study matter under conditions far beyond anything we can achieve on Earth without hitting the ultimate breakdown point that a singularity represents. For astrophysicists and cosmologists, this makes gravastars not just curiosities, but potentially crucial tools for understanding the fundamental forces of the universe. Furthermore, the absence of a singularity highlights the philosophical implications of gravastars. Black holes are often viewed as the universe's ultimate no-go zones, places where physical reality ends. Gravastars, in contrast, suggest that nature might avoid such absolute endings. Instead of destruction and erasure, we could be looking at objects where equilibrium is maintained under extreme tension. This opens the door to thinking about the cosmos not just in terms of catastrophic endpoints, but in terms of delicate balances that preserve information, energy, and space-time itself. By replacing the singularity with a vacuum energy core, gravastars present a radically different picture of how extreme gravitational collapse might manifest. They demonstrate that the universe may have ways of containing its most powerful forces without resorting to infinities or breaking its own rules. This makes them intellectually fascinating, scientifically promising, and deeply unnerving. They are objects that appear calm and stable but carry the latent potential for catastrophic energy release, all while hiding a complexity that challenges our understanding of physics at its most extreme. The scientific fascination with gravastars goes far beyond their exotic structure or potential for cosmic catastrophe. It is deeply intertwined with one of the most perplexing puzzles in modern physics, the black hole information paradox. To understand why gravastars capture the imagination of physicists, we need to explore the paradox itself, its implications, and how gravastars could provide a potential resolution. The information paradox arises from a fundamental clash between quantum mechanics and general relativity. According to general relativity, when matter collapses into a black hole, it inevitably ends up at a singularity, a point of infinite density where space-time curvature becomes infinite. Classical black holes, described by Einstein's equations, possess an event horizon that effectively seals off anything inside, including the information about the matter that has fallen in. From a relativistic standpoint, the information is inaccessible, and once it crosses the horizon, it appears lost forever. Quantum mechanics, however, operates under a strict principle: information cannot be destroyed. The exact state of every particle and the interactions that lead to any given outcome must, in theory, be recoverable. The apparent loss of information in black holes is therefore a direct violation of quantum theory. Stephen Hawking, in the 1970s, showed that black holes emit what is now called Hawking radiation, a faint thermal radiation due to quantum effects near the event horizon. This radiation, while allowing black holes to slowly lose mass and potentially evaporate, does not seem to carry the detailed information about the particles that originally fell into the black hole. Hence, the paradox: either quantum mechanics is incomplete, or our understanding of black holes is fundamentally flawed. Enter gravastars. By eliminating the singularity at the core, gravastars offer a potential escape hatch from this paradox. Because matter is never crushed into an infinitely dense point, and because there is no true event horizon in the traditional sense, information may not be irretrievably lost. Instead, it could be stored within the ultra-dense shell or in the vacuum energy core, potentially allowing it to be released back into the universe under certain circumstances. In effect, gravastars preserve the causal structure of spacetime in a way that black holes do not, offering a scenario where quantum information could, at least in principle, survive extreme gravitational collapse. This possibility excites physicists because it provides a framework to reconcile the seemingly incompatible laws of quantum mechanics and general relativity. If gravastars exist, they could serve as a laboratory for testing ideas about quantum gravity, the elusive theory that attempts to unify these two pillars of modern physics. By modeling how information might be stored or slowly emitted from a gravastar, scientists could gain insights into the deep interplay between gravity and quantum theory, perhaps shedding light on how the universe maintains consistency in its fundamental laws, even under extreme conditions. Beyond the purely theoretical, the resolution of the information paradox has practical implications for our understanding of the universe. If black holes truly destroy information, then predicting the evolution of the universe at a fundamental level becomes impossible in regions affected by black holes. Gravastars, by offering an alternative, suggest that the universe may be far more orderly than black hole physics alone would indicate. They hint that extreme gravitational collapse may not represent a breakdown of natural laws but a different kind of organization that preserves information while hiding it from casual observation. The potential information-preserving properties of gravastars also raise fascinating questions about observational consequences. If information can escape, even indirectly, it could influence the behavior of surrounding matter and radiation in subtle ways. For instance, infalling matter could interact with the shell or vacuum core, emitting energy or particles in patterns different from those expected around traditional black holes. Detecting such anomalies could provide indirect evidence for gravastars and offer a way to test their information-preserving properties. These are the kinds of observational signatures that astronomers are beginning to search for using advanced telescopes and gravitational wave detectors. Furthermore, the gravastar's approach to resolving the information paradox challenges some long-held assumptions about the final fate of massive stars. Traditionally, stars above a certain mass threshold are thought to inevitably form black holes, where all the information about their collapse is lost beyond the event horizon. Gravastars offer an alternative narrative. A collapsing star might stabilize as a gravastar, storing its information in a complex internal structure rather than allowing it to vanish into a singularity. This reframing forces scientists to reconsider not only the endpoints of stellar evolution but also the broader architecture of the cosmos, where the fate of information could be far more subtle and intricate than previously imagined. It's also important to note that gravastars could provide insights into phenomena that black holes cannot easily explain. For example, the mysterious nature of gamma-ray bursts, the behavior of certain accretion disks, or the peculiarities in gravitational wave signals might be more readily understood if some of the objects we classify as black holes are actually gravastars. The ability of gravastars to preserve information could correlate with these unusual energetic behaviors, offering a potential link between fundamental theory and observable cosmic events. In essence, scientists care about gravastars not because they are guaranteed to exist, but because they represent a profound conceptual bridge between two of the most successful yet seemingly incompatible theories in physics. They offer a concrete alternative to the troubling notion that information is lost in black holes, potentially saving the consistency of quantum mechanics without violating general relativity. This dual promise, resolving theoretical paradoxes while suggesting new avenues for observation, makes gravastars uniquely compelling. Finally, the very act of considering gravastars forces scientists to confront the limits of our current understanding. They highlight the extraordinary conditions under which our models of physics are tested, where density, pressure, energy, and gravity reach extremes far beyond what we can replicate on Earth. By exploring gravastars, physicists are pushed to think creatively, to develop new mathematical tools, and to expand the boundaries of theoretical and observational astronomy. In this sense, gravastars are as much about the journey of discovery as they are about the destination. They are a challenge to human understanding, daring us to probe the most extreme possibilities the universe might hide. If gravastars truly exist, their most unnerving quality may not be their internal structure or exotic energy core. It could be how deceptively similar they are to black holes while secretly behaving in entirely different ways. From a distance, a gravastar might look almost indistinguishable from a black hole. They could bend light in the same way, affect nearby stars similarly, and even generate gravitational waves reminiscent of black hole mergers. To an astronomer relying on indirect observation, a gravastar might masquerade as just another black hole, hiding its extraordinary differences in plain sight. This mimicry is terrifying because it undermines the assumption that we truly know the nature of the objects we observe in the cosmos. For decades, astronomers have classified objects based on gravitational effects, the movement of nearby stars, and radiation from accretion disks. Black holes were considered the only plausible explanation for these extreme phenomena. But if some of these objects are gravastars instead, it means we might have been misidentifying cosmic monsters all along, mistaking something far more complex, and potentially far more dangerous, for what we thought was a well-understood black hole. One of the key sources of unease comes from the subtle yet profound differences in behavior. While black holes consume matter inexorably, once inside the event horizon, nothing escapes. Gravastars, on the other hand, lack a true singularity and may not have a conventional event horizon. Instead, they trap light and matter temporarily, often for extremely long periods, before potentially releasing it in unpredictable ways. Imagine a star's collapse producing an object that appears inert but, under certain conditions, could suddenly expel enormous amounts of energy. To any nearby solar system, this could be catastrophic. A gravastar might look calm, but its underlying instability hides a latent power that could rival or surpass supernovae. Another aspect of this unsettling behavior is tied to gravitational waves. When black holes merge, the waves they produce follow very specific patterns, predictable according to general relativity. Gravastars, however, could generate echoes in gravitational waves that differ from these patterns. These echoes are subtle, faint reverberations caused by the interaction of the ultradense shell with the surrounding spacetime, and they might persist for longer periods than expected. Detecting such anomalies could provide a clue that the object is not a black hole, but the fact that these echoes could be hidden among cosmic noise adds a layer of danger. We might never be entirely sure which objects are hiding gravastar-like properties. Perhaps the most frightening possibility is the potential for explosive instability. A gravastar's delicate balance is maintained by the interplay of vacuum energy pushing outward and gravity pulling inward. If this balance were disrupted, through the accretion of matter, collision with another massive object, or internal fluctuations, the result could be catastrophic. Unlike black holes, which are effectively eternal and steadily devour anything nearby, a gravastar could implode or explode, releasing enormous amounts of energy in a sudden burst. This is a fundamentally different kind of threat, one where an object that seemed stable could transform into a cosmic bomb without warning. Even more disconcerting is the philosophical and observational uncertainty surrounding gravastars. In essence, they are cosmic objects that combine familiarity with extreme unpredictability. They force us to reconsider what we know about the universe. If many of the black holes we've observed are actually gravastars, our understanding of stellar evolution, galaxy dynamics, and even the life cycle of matter may need to be re-examined. Every prediction made about the behavior of a black hole at the center of a galaxy, for example, could be subtly off if that object is a gravastar instead. This uncertainty, the possibility that the universe's most powerful objects are operating according to rules we don't fully understand, is, in itself, deeply unsettling. The mimicry extends to light-bending effects as well. Gravastars' ultradense shells and vacuum cause warp spacetime so intensely that light passing nearby can circle them, producing effects almost identical to gravitational lensing caused by black holes. From a distance, an observer might see stars orbiting an invisible mass, detect accretion disks glowing in X-rays, and conclude they are looking at a black hole, when in fact they are witnessing the subtle, hidden mechanics of a gravastar. The universe could be filled with these imposters, perfectly camouflaged yet capable of behaving in entirely unpredictable ways. Additionally, gravastars challenge the notion of inevitability in cosmic destruction. Black holes have a simple, terrifying logic: anything that crosses the event horizon is lost forever. Gravastars, with their nuanced dynamics, could unpredictably eject matter or radiation back into the universe. The timing, direction, and magnitude of such events would be impossible to predict accurately. For civilizations located near such objects, even if unknowingly, the threat would be immense. A sudden release of energy could destabilize planetary orbits, obliterate nearby stars, or trigger cascading cosmic phenomena without any prior warning signs. Finally, the terrifying aspect is psychological as much as it is physical. Humans are wired to fear the unknown, and gravastars embody that unknown in spades. They are objects that appear to be familiar, behave almost like well-studied black holes, yet contain internal structures and energy potentials that defy our expectations. They are cosmic wolves in sheep's clothing, and the possibility that they are real forces a humbling acknowledgement. The universe may be far stranger and more dangerous than even our most vivid theories have dared to imagine. Gravastars challenge one of the most defining features of black holes: the event horizon. A black hole's event horizon is a one-way boundary in spacetime. Cross it, and nothing, not even light, can escape. This boundary is absolute, sealing off the singularity from the rest of the universe and creating the iconic point of no return. Gravastars, however, introduce a subtle but profound difference. They may lack a true event horizon in the strictest sense, yet they are still capable of trapping light and matter for astonishingly long periods. This property both mimics the behavior of black holes and introduces a host of unique consequences. The reason gravastars can trap light without a true event horizon lies in their structural composition. The ultra-dense shell surrounding the vacuum energy core produces extreme spacetime curvature. Light that ventures too close can be caught in orbit around the shell, circling the gravastar in paths that, from a distant observer's perspective, appear nearly stationary. This phenomenon, sometimes described as a photon sphere, allows gravastars to act as optical traps, creating the illusion of a black hole even though photons could, theoretically, eventually escape. The timescale for escape could be astronomically long, millions or even billions of years, making them observationally indistinguishable from black holes for practical purposes. This quasi-event horizon effect has profound implications. To an observer using conventional astronomical tools, a gravastar might exhibit many of the same signatures as a black hole: light from nearby stars bending dramatically, matter swirling in accretion disks, and intense X-ray emissions from heated gas. In many ways, the universe itself may be deceiving us, presenting gravastars as familiar black holes while hiding the subtle differences that could reveal their true nature. The optical illusion is so convincing that distinguishing between the two becomes a challenge at the forefront of observational astrophysics. Yet the lack of a true event horizon introduces a critical difference in physics and potential danger. In black holes, once an object crosses the horizon, its information is effectively trapped forever, and the singularity ensures that all mass is compacted into an infinitely dense point. Gravastars, in contrast, store energy and information in the dense shell and vacuum core rather than in a singularity. This opens up the theoretical possibility of eventual energy or matter release. Even though the timescales might be staggeringly long, it introduces a type of uncertainty that is entirely absent in classical black holes. In other words, gravastars behave like black holes for billions of years but might harbor the potential to unleash their contents under the right conditions. The comparison also raises intriguing observational questions. Gravitational lensing near a gravastar would closely resemble that of a black hole, making it hard to detect differences through light alone. However, researchers have proposed that gravitational waves could provide subtle clues. In mergers involving gravastars, the lack of a true event horizon could generate echoes in the post-merger signal, faint, repeated ripples that gradually fade rather than the singular ring-down pattern characteristic of black hole mergers. These echoes, if detected, could offer the first empirical evidence that some of the objects we currently classify as black holes are, in fact, gravastars masquerading behind quasi-horizons. The quasi-event horizon also affects the behavior of accreting matter. While matter falling toward a black hole vanishes past the event horizon, matter approaching a gravastar's dense shell could interact in complex ways. It might be compressed, heated, or even temporarily rebound, producing radiation patterns that differ subtly from those near a classical black hole. These differences could manifest as anomalous X-ray or gamma-ray emissions, clues that astronomers are beginning to investigate using advanced space-based observatories. The challenge is that the deviations are subtle, often requiring incredibly precise measurements to detect. Even then, they could be confounded by other cosmic phenomena, making the task of distinguishing gravastars from black holes a monumental observational challenge. From a theoretical standpoint, the absence of a true event horizon introduces fascinating consequences for the nature of time and causality. In black holes, the event horizon creates an absolute temporal boundary. Time effectively stops at the singularity from the perspective of an external observer. Gravastars, lacking such a horizon, allow time and information to remain well-defined everywhere outside the core. This could fundamentally alter our understanding of how gravity and quantum mechanics interact under extreme conditions, offering a potential laboratory for probing some of the most profound questions in physics. Despite these differences, the danger posed by gravastars remains immense. Their quasi-horizon creates a tension. They behave like black holes entrapping light and matter, but the possibility of eventual release of energy or matter means they are not entirely predictable. A gravastar that appears inert could, under extreme conditions, release massive bursts of energy, with catastrophic consequences for anything nearby. This uncertainty, combined with their observational mimicry, makes gravastars particularly terrifying, an invisible threat that could exist anywhere we currently assume a black hole dominates. In practical terms, imagine the Milky Way's central black hole, Sagittarius A star. If it were a gravastar rather than a black hole, the implications would be staggering. Stars orbiting near the center might behave as expected for now, but the potential energy stored in the vacuum core could, theoretically, be released in the distant future, producing radiation, shockwaves, or gravitational disturbances far beyond what we anticipate. Even more subtle, the gradual leakage of information and energy from the gravastar could affect the dynamics of the galaxy in ways that challenge current astrophysical models. In short, gravastars blur the line between a cosmic prison and a latent energy reservoir. They trap light and matter with the eerie efficiency of a black hole but without the absolute finality of an event horizon. This quasi-trap allows them to appear harmless or stable for incomprehensibly long periods, all the while storing and manipulating energy in ways that remain largely theoretical but deeply consequential. Observationally, they are indistinguishable from black holes, yet conceptually, they introduce a universe of new possibilities, dangers, and unknown behaviors that challenge our understanding of the cosmos. If a gravastar were to replace a black hole, the potential dangers could be both subtle and catastrophic, stemming from the fact that its internal dynamics are fundamentally different from a black hole's. Unlike black holes, which steadily consume matter and lock it away behind an event horizon, gravastars store energy in their dense shells and vacuum-like cores. This energy is stabilized by the delicate equilibrium between the outward push of vacuum energy, sometimes likened to dark energy, and the inward pull of gravity. But this balance is precarious. Any significant disturbance, whether from infalling matter, gravitational interactions, or internal instabilities, could disrupt the equilibrium, potentially unleashing energy on a colossal scale. Imagine a massive star spiraling toward what we thought was a black hole at the center of a galaxy, only to find that the object is actually a gravastar. As matter accumulates around the dense shell, it increases pressure and tension within the gravastar's structure. Unlike a black hole, which absorbs this matter quietly and efficiently, the gravastar could reach a tipping point. At this moment, the stored energy might be released explosively, emitting radiation or ejecting matter at velocities approaching the speed of light. This is not just a theoretical concern. Such an event would dwarf most known astrophysical phenomena, potentially rivaling or exceeding the energy released by supernovae or gamma-ray bursts. The danger lies not only in the scale of the energy release but also in its unpredictability. Black holes are, in a sense, safe in their finality. Once matter crosses the event horizon, it is irretrievably absorbed, and the dynamics around the black hole follow well-established patterns. Gravastars, by contrast, could behave differently depending on subtle changes in their internal structure or the surrounding environment. Even minor gravitational perturbations from a nearby star or passing massive object might be enough to disturb the shell's balance, triggering partial or full energy release. This makes gravastars more capricious than black holes. They don't just consume, they also have the potential to erupt. The energy release from a gravastar could take many forms. One possibility is a sudden burst of electromagnetic radiation, ranging from X-rays to gamma rays. These bursts could be intense enough to affect the interstellar medium, heat nearby stars, or even disrupt planetary systems. Another potential danger involves gravitational waves. A sudden structural reconfiguration or collapse of the gravastar could generate ripples in spacetime far stronger than the steady gravitational waves produced by a merging black hole pair. These waves, propagating across the galaxy, could have subtle but measurable effects on orbiting bodies and on the trajectory of surrounding matter. This potential for explosive behavior also makes gravastars a candidate explanation for some of the universe's most mysterious high-energy phenomena, such as certain gamma-ray bursts that don't fit conventional models. If a gravastar's core energy was suddenly released, it could account for the immense energy output observed in these bursts, occurring without the apparent presence of a supernova or black hole collision. This possibility hints at a universe filled with hidden ticking time bombs, whose presence we might not even suspect until one detonates in spectacular fashion. Furthermore, the energy release could have cascading effects on nearby stars and solar systems. The gravitational equilibrium around the gravastar could shift abruptly, altering orbits, destabilizing accretion disks, or ejecting matter into interstellar space. Even systems located many light-years away could experience dramatic consequences if the gravastar releases energy in the form of a shockwave or directed radiation. In a sense, a gravastar is not just a passive cosmic object, it is a potential agent of destruction, capable of reshaping its local stellar neighborhood under the right conditions. This unpredictability is compounded by our observational limitations. From our vantage point on Earth, many gravastars could be masquerading as black holes, making it impossible to anticipate which objects might be prone to sudden energy release. Astronomers rely on indirect observations, such as the motion of nearby stars or X-ray emissions from accretion disks, to infer the presence of black holes. If gravastars are hiding among these observations, the very tools we use to monitor cosmic threats might fail to detect the most dangerous objects in the galaxy. In essence, a gravastar could appear calm and stable for eons, only to erupt in a cosmic spectacle of destruction without warning. The potential hazards also extend to human understanding and technology. Imagine we were able to send probes or observe up close the center of a galaxy, assuming a black hole governs the region. A gravastar, storing unimaginable amounts of energy in its vacuum core, could release this energy in a way that not only jeopardizes our instruments but also provides a completely unexpected insight into physics at extreme conditions. The very properties that make gravastars fascinating to physicists, their dense shells, vacuum cores, and quasi-event horizons, also make them unpredictable cosmic phenomena capable of sudden, catastrophic energy discharges. This threat is magnified by the hypothetical possibility of collapse scenarios. If the delicate balance between the inward gravitational pull and the outward vacuum energy were to fail, the gravastar could undergo a sudden structural collapse, converting its stored energy into kinetic energy and radiation. Such an event might produce a burst of light and energy more powerful than any known supernova, spreading out across space with devastating intensity. Unlike black holes, which quietly maintain their singularity, gravastars introduce an element of suspense. The object appears stable, but the potential for catastrophic release always exists. In short, The dangers of a gravastar replacing a black hole are multifaceted. They combine the deceptive calm of mimicry with the explosive potential of latent energy, creating objects that are simultaneously invisible threats and time bombs. This duality, appearing inert while holding the potential for extreme energy release, is what makes gravastars profoundly terrifying. They are cosmic enigmas whose true nature might only be revealed through sudden, catastrophic events, challenging both our observational abilities and our understanding of astrophysical stability. The collapse scenario of a gravastar is one of the most dramatic and unsettling possibilities in theoretical astrophysics. Unlike black holes, which are governed by a singularity that quietly absorbs matter and energy, gravastars rely on a precarious balance between the inward pull of gravity and the outward push of vacuum energy in their cores. This balance is delicate, and if disrupted, the consequences could be cataclysmic. Imagine a structure spanning kilometers, holding within it energy far exceeding anything humans have ever witnessed, suddenly destabilizing. The resulting explosion could be a cosmic event of unparalleled scale. The instability could arise from several factors. A gravastar accumulates matter from its surroundings, either through stellar accretion or collisions with other compact objects. Each added mass slightly shifts the equilibrium, pressing the dense shell inward while the vacuum core continues to push outward. Normally, this tug-of-war remains stable over immense timescales. However, if the shell's structural integrity fails, whether through accumulated stress, tidal interactions with another massive object, or quantum fluctuations at the boundary layer, the core's vacuum energy could erupt uncontrollably. The result would not just be a collapse but a violent ejection of energy and matter into the surrounding space. Unlike a supernova, which is fueled by nuclear reactions, a gravastar explosion would be driven by the conversion of vacuum energy into kinetic and radiative forms. This energy is stored in the vacuum-like core, which behaves analogously to dark energy in cosmological models, pushing outward with immense pressure. Once the restraining shell fails, there is nothing to contain this energy, leading to a near-instantaneous expansion outward at relativistic speeds. Matter in the shell and any infalling material could be accelerated to fractions of the speed of light, accompanied by bursts of high-energy photons such as X-rays and gamma rays. This type of explosion would dwarf conventional stellar events in both energy and impact radius. The collapse could also generate a spectacular gravitational wave signature. In a black hole merger, the event horizon smooths out the post-merger spacetime, producing a characteristic ringdown. A gravastar's collapse, however, would likely create a more chaotic pattern. Sudden shifts in mass distribution, explosive expansion of the shell, and the rapid release of energy from the vacuum core could generate waves with echoes and reverberations, potentially detectable across vast distances. Such signals might provide the first observational evidence that gravastars exist, though distinguishing them from other violent cosmic events would be challenging. The explosion would not necessarily destroy the gravastar entirely. Depending on the dynamics, portions of the dense shell could be ejected while the vacuum core contracts or reforms, creating a remnant with a new configuration. This could lead to recurring instabilities or repeated bursts of energy, akin to a pulsating cosmic engine. Such behavior would be unlike anything seen in black holes, where the singularity ensures that the structure is final and unchanging, and it would make gravastars unpredictable even over timescales of millions of years. Nearby celestial objects would face immense risks. Stars in the vicinity could be stripped of their outer layers, planetary systems could be destabilized, and interstellar gas could be heated or expelled at extreme velocities. The energy output of a collapsing gravastar could rival or surpass the largest observed supernovae, turning a localized region of a galaxy into a cauldron of high-energy particles and radiation. Even if the explosion were partially contained, the gravitational shockwaves alone could alter the orbits of nearby stars and planets, creating chaos on a galactic scale. Interestingly, the collapse scenario might also provide an explanation for some of the most enigmatic cosmic phenomena. Certain gamma-ray bursts, which appear to emit more energy than a typical supernova yet lack an obvious progenitor, could potentially originate from a gravastar destabilization. In these cases, the energy stored in the vacuum core is suddenly released, producing a burst so intense that it temporarily outshines entire galaxies. Unlike black hole mergers or neutron star collisions, a gravastar collapse would offer a mechanism for these extreme events without requiring the formation of a singularity. The concept of a collapse also challenges our understanding of the life cycle of compact objects. Traditional models consider stellar evolution ending in a stable black hole or neutron star, but gravastars introduce a new class of endpoints, objects that are stable only conditionally and capable of violent reconfiguration. This unpredictability forces astrophysicists to rethink how galaxies evolve over billions of years, as one of these hidden objects could radically alter the environment if its internal balance is disturbed. From a human perspective, the implications are staggering, though fortunately cosmic distances provide some safety. A gravastar in our own galaxy, if it were to collapse, could emit energy that would affect the interstellar medium and potentially reach the solar system in the form of radiation or gravitational waves. While such an event is extraordinarily unlikely on human timescales, the theoretical possibility underscores the terrifying nature of these objects. They appear calm, indistinguishable from black holes, yet contain a latent power that could reshape their surroundings in an instant. The collapse scenario also forces a re-evaluation of energy storage in extreme environments. Unlike black holes, which absorb energy irretrievably, gravastars accumulate it in a structured form, creating a reservoir that could be unleashed under the right conditions. This controlled instability introduces both danger and opportunity for scientists seeking to understand the physics of extreme matter and energy, potentially offering a natural laboratory for probing phenomena that are otherwise inaccessible. In summary, the violent collapse of a gravastar represents one of the most fearsome possibilities in the universe. It is a scenario where the combination of immense vacuum energy, a precarious structural shell, and external perturbations could result in a cosmic explosion unmatched in scale. The unpredictability, potential for energy release, and observational disguise make gravastars not only a theoretical curiosity but a profound cosmic threat, lurking silently in the shadows of space, awaiting a moment when the balance tips and unleashes their full power. One of the most tantalizing possibilities about gravastars is their potential link to gamma-ray bursts, GRBs, the universe's most energetic explosions. These bursts of high-energy radiation are so powerful that a single event can release, in seconds, more energy than the Sun will emit over its entire 10 billion-year lifetime. For decades, astronomers have sought to explain the origins of GRBs, attributing many to massive stellar collapses or collisions between neutron stars. Yet, certain bursts remain enigmatic, showing extreme energy outputs without clear progenitor events, leaving scientists puzzled. Here, gravastars enter the picture as a compelling theoretical solution. The central idea hinges on the unique structure and energy dynamics of a gravastar. Unlike black holes, which trap matter and energy irretrievably behind an event horizon, gravastars contain a vacuum-like core filled with repulsive energy, akin to dark energy, stabilized by an ultra-dense shell. This core can store incredible amounts of energy over cosmic timescales, acting almost like a compressed battery of space-time energy. Should the delicate balance between the outward pressure of this vacuum energy and the inward pull of gravity be disrupted, the energy could be released in a sudden, violent eruption. The resulting explosion could easily match the energy observed in GRBs. Unlike conventional sources of gamma-ray bursts, which typically involve matter being compressed into a singularity, the gravastar mechanism allows for energy release without a singularity. The collapse or rupture of the dense shell could unleash photons directly from the vacuum core or accelerate surrounding matter to near-light speeds, producing extremely high-energy gamma rays. This offers a potential explanation for the ultra-bright, short-duration bursts that sometimes appear in unexpected regions of space where no recent supernova or stellar merger has been detected. In other words, gravastars could be the hidden engines behind GRBs that don't fit standard models. The timing and variability of GRBs also align intriguingly with the gravastar hypothesis. Some gamma-ray bursts display multiple peaks or quasi-periodic structures, suggesting that the energy release was not a single instantaneous event but occurred in stages. A gravastar's shell might crack or oscillate under stress, releasing energy intermittently as the vacuum core readjusts to maintain equilibrium. This could naturally produce the observed burst patterns, giving astronomers a plausible mechanism for the complex light curves seen in many GRBs. Furthermore, gravastars might explain why some gamma-ray bursts occur in regions with minimal stellar activity. Traditional explanations often require a massive star to collapse or two neutron stars to collide, yet astronomers have detected intense bursts in seemingly quiet areas of the universe. If a gravastar resides undetected in such regions, storing immense energy silently for millions or even billions of years, its sudden collapse could produce a GRB without any accompanying supernova, matching the observed anomalies. Another aspect involves the extreme collimation of gamma-ray bursts. Observations suggest that GRBs are often tightly focused jets of energy, which could be naturally accounted for by the directional dynamics of a gravastar's shell collapse. If the ultra-dense shell fractures asymmetrically, the vacuum core energy would be released preferentially along specific axes, creating narrowly focused beams of gamma rays that could travel across vast intergalactic distances. This mechanism could explain the incredible intensity of bursts observed from billions of light-years away, where the energy seems concentrated rather than diffused. The potential link between gravastars and GRBs also intersects with gravitational wave astronomy. Some gamma-ray bursts are observed in tandem with gravitational waves, hinting at catastrophic astrophysical events. A gravastar collapse could theoretically produce both. A sudden reconfiguration of the dense shell would emit gravitational waves while the vacuum energy escape generates a gamma-ray burst. The pattern of these gravitational waves might differ subtly from those produced by black hole mergers, providing a potential observational signature that distinguishes gravastar-driven GRBs from other sources. Detecting such a signature would be groundbreaking, offering indirect evidence for the existence of these mysterious objects. The energetic implications are staggering. A gravastar-induced GRB could release enough energy to affect not just the immediate surroundings but potentially the interstellar medium across light-years, heating gas, triggering shockwaves, and influencing star formation in nearby regions. The scale of destruction and influence rivals that of other cosmic catastrophes, making gravastars not only fascinating theoretical objects but also potentially significant players in the evolution of galaxies. Yet the link between gravastars and gamma-ray bursts remains purely speculative. No direct evidence of gravastars exists, and the mechanisms described are inferred from theoretical models of vacuum energy, shell dynamics, and general relativity. However, this hypothesis elegantly explains some of the anomalies in GRB observations: extremely high energy, short duration, unexpected locations, and structured light curves that standard models struggle to reconcile. In this sense, gravastars represent both a challenge and an opportunity for astrophysicists, a chance to rethink the origins of some of the universe's most violent and enigmatic phenomena. Moreover, considering gravastars as GRB progenitors opens up new avenues for observation. Astronomers could search for gamma-ray bursts in regions with minimal stellar activity, look for unusual gravitational wave signatures accompanying bursts, or analyze energy spectra for patterns indicative of vacuum core-driven explosions. Each of these strategies might provide indirect evidence that the universe harbors gravastars, hiding in plain sight while occasionally revealing their presence through extreme, high-energy phenomena. In short, gravastars offer a tantalizing solution to one of astrophysics' most persistent mysteries: unexplained gamma-ray bursts. Their theoretical ability to store enormous amounts of vacuum energy and release it suddenly in catastrophic bursts makes them uniquely suited to explain these events. If even a fraction of GRBs originate from gravastars, it would transform our understanding of cosmic high-energy phenomena, suggesting that the universe contains hidden engines far stranger and more powerful than we had ever imagined. The concept of energy storage in a gravastar is one of the most fascinating and potentially terrifying aspects of these hypothetical objects. Unlike conventional stars, which generate energy through nuclear fusion, or black holes, which trap matter and energy irreversibly behind an event horizon, gravastars are theorized to contain a central core of vacuum-like energy, often compared to dark energy. This core is not merely a passive feature. It functions as an enormous reservoir, compressing energy into a state that is incomprehensible by everyday human standards. The potential magnitude of this energy makes gravastars among the most exotic and dangerous theoretical objects in the universe. The vacuum core arises from a state of spacetime in which energy density is uniform and negative in terms of pressure, a phenomenon familiar in cosmology as dark energy. In a gravastar, this vacuum energy exerts an outward pressure that counteracts the immense gravitational pull of the ultradense shell surrounding it. In essence, the core is a cosmic battery, storing energy not in matter but in the very fabric of spacetime itself. This is fundamentally different from ordinary energy storage, because no conventional material container could survive the conditions inside a gravastar. Instead, the container is spacetime itself, held together by the balance between inward gravity and outward vacuum pressure. The energy density of the vacuum core can be astonishing. While precise calculations are impossible without observing a real gravastar, theoretical models suggest that the energy content could easily surpass the total energy output of a supernova or even a gamma-ray burst. To visualize it, imagine compressing the combined mass energy of millions of suns into a compact sphere just a few kilometers across. The core's energy is not inert. It exists in a state capable of immediate conversion into radiation or kinetic energy if the balance is disturbed. This makes the gravastar not just a passive object of extreme density but a potential cosmic bomb, waiting for a trigger that could release its energy catastrophically. The mechanism for storing this energy relies on the interplay between general relativity and quantum effects in curved spacetime. Unlike ordinary matter, which is subject to nuclear and chemical constraints, the vacuum energy in a gravastar's core exists due to the unique properties of space itself. This means the energy can be accumulated indefinitely without the thermal or mechanical degradation that limits conventional energy storage. In principle, the core could remain stable for billions of years, quietly containing energy at a scale that is virtually unimaginable, until some perturbation triggers its release. One of the most striking aspects of this energy storage is its stability. The outward pressure from the vacuum core is precisely counteracted by the inward gravitational pull of the dense shell, creating a finely tuned equilibrium. As long as this balance persists, the energy remains trapped, unable to escape into surrounding space. But the same stability is what makes it so terrifying. A sudden collapse or rupture of the shell could convert this enormous reservoir of vacuum energy into radiation, particle acceleration, and gravitational waves almost instantaneously. The release could be far more powerful than any known astrophysical event, dwarfing even the largest supernovae or the brightest gamma-ray bursts. Furthermore, the storage of energy in this manner challenges conventional notions of what energy is in the universe. In most contexts, energy is associated with matter or radiation. In a gravastar, energy is stored directly in the vacuum of space, highlighting a fundamental difference between this hypothetical object and anything observed in the universe so far. This has profound implications for physics. It suggests that under extreme conditions, the fabric of spacetime itself can act as both a container and a source of tremendous power, providing a natural laboratory for studying the intersection of quantum theory, general relativity, and cosmology. Theoretical models also suggest that the vacuum energy could fluctuate due to quantum effects, even in a stable gravastar. These fluctuations are usually negligible, but in an extreme scenario, they might act as a catalyst for instability, nudging the system toward collapse or energetic release. This adds another layer of unpredictability to gravastars. The energy is stored safely for eons, but the underlying quantum properties of spacetime could make catastrophic release not impossible, just incredibly rare. Importantly, the energy stored in a gravastar's vacuum core is fundamentally different from that of a black hole. Black holes absorb matter and energy, locking it behind an event horizon where it cannot influence the outside universe except through gravity. In contrast, the energy in a gravastar is compressed but poised for interaction. It is contained in a way that could, under the right circumstances, be explosively liberated. This is what makes gravastars so uniquely dangerous. They combine the invisibility and compactness of black holes with an active, potentially volatile energy reservoir. From an observational perspective, this stored energy complicates efforts to detect gravastars. Because the energy is trapped, a gravastar can remain virtually invisible, only revealing its presence indirectly through gravitational effects or, in extreme cases, through bursts of radiation if the core's energy is released. This stealthy energy storage, combined with the potential for catastrophic release, creates an object that is as elusive as it is threatening, a silent, invisible powerhouse lurking in the cosmos. Ultimately, the vacuum core of a gravastar represents one of the most mind-bending concepts in theoretical astrophysics. It is a structure that stores vast amounts of energy in the very fabric of spacetime, balanced delicately by gravity, and capable of releasing that energy in ways that could reshape its surroundings across light years. The sheer magnitude of this stored energy, coupled with the potential for sudden, unpredictable release, positions gravastars as some of the most fearsome theoretical objects in the universe, capable of cosmic-scale disruption that humanity is only beginning to imagine. Gravastars are notoriously difficult to distinguish from black holes, and this observational challenge is one of the reasons they remain purely theoretical to this day. At first glance, a gravastar might appear almost identical to a black hole from an astronomical perspective. Both are extremely compact objects with immense gravitational influence, capable of bending light and warping spacetime to extreme degrees. For astronomers using telescopes to observe distant galaxies, star systems, or galactic centers, the subtle differences between these two cosmic phenomena are extremely difficult to detect. The primary reason for this difficulty lies in the behavior of light near these objects. In black holes, the event horizon represents a point of no return. Light and matter that pass this boundary cannot escape. Gravastars, by contrast, may not have a true event horizon, yet they still possess an incredibly strong gravitational field that can trap light for extraordinarily long periods. Light emitted near the surface of a gravastar would still struggle to escape, producing an observational signature nearly identical to that of a black hole. To a distant observer, both objects would appear as dark, shadowy silhouettes against the glowing backdrop of surrounding stars and accreting material. Moreover, the accretion of matter around gravastars further complicates observation. Just like black holes, gravastars can pull in gas, dust, and even whole stars from their surroundings. As this matter spirals inward, it heats up and emits intense radiation, particularly in X-ray and gamma-ray wavelengths. These accretion signatures dominate what telescopes detect, often overshadowing the subtle differences in the underlying structure of the central object. The radiation patterns from accreting gravastars could mimic those of black holes so closely that even high-resolution observatories like the Chandra X-ray Observatory or the Event Horizon Telescope might struggle to tell the difference. Another layer of complexity comes from gravitational lensing. Both black holes and gravastars bend light around them due to their extreme mass, creating distortions in the observed images of background stars or galaxies. The lensing effects from a gravastar's ultra-dense shell can be almost indistinguishable from those produced by a black hole of similar mass. This means that even sophisticated techniques designed to map the shadow of a black hole, like the famous image of M87's central black hole, could potentially be observing a gravastar without realizing it. The subtle differences in light paths near the surface are often smaller than the resolution limits of current instruments, leaving astronomers with uncertainty. Gravitational waves provide another potential, yet challenging, avenue for differentiation. When two compact objects merge, they produce ripples in space-time that can be detected across the universe. The gravitational wave signatures of black hole mergers are relatively well understood, but a merger involving a gravastar might produce slightly different echoes due to the presence of the ultra-dense shell and vacuum core. However, these differences are extremely subtle and require detectors with unprecedented sensitivity to discern. While LIGO and Virgo have revolutionized astrophysics by detecting gravitational waves, current technology may only provide indirect hints at best, leaving the existence of gravastars unresolved. The challenge also extends to modeling and theory. Black holes are well described by the equations of general relativity and have decades of observational data supporting their existence. Gravastars, on the other hand, are based on theoretical constructs and require precise balancing of forces in a vacuum energy core and ultra-dense shell. Even if a gravastar exists, its appearance and behavior could vary depending on the specific parameters of its shell thickness, mass, and vacuum energy density. This variability adds another layer of uncertainty for astronomers attempting to identify these objects in real observations. Additionally, the timescales involved pose a challenge. Any dynamic behaviors unique to gravastars, such as oscillations of the shell or slow leakage of vacuum energy, might occur over millions or billions of years, timescales far exceeding human observation periods. This means that many distinguishing features, if they exist at all, could be imperceptible within the window of observation available to astronomers today. The object could remain virtually indistinguishable from a black hole for the entire time humans are observing it. Even the most precise measurements of orbital motion in nearby stars provide only indirect evidence. Stars orbiting the center of the Milky Way, such as those around Sagittarius A*, reveal a massive, compact object, but they cannot reveal whether the object is a black hole with an event horizon or a gravastar with a vacuum core. The gravitational influence is identical in the regime detectable with current instruments. Unless a gravastar undergoes a sudden energetic event, such as a shell collapse or vacuum energy release, it could remain hidden indefinitely. This observational challenge also touches on the philosophical limits of astronomy. In many ways, distinguishing between black holes and gravastars pushes the boundary of what we can infer about the universe based on indirect evidence. We rely on light, radiation, gravitational waves, and motion of nearby matter to understand distant objects. If two fundamentally different objects produce nearly identical observational signatures, we are forced to confront the limits of empirical detection. Gravastars exemplify this dilemma. They might be lurking throughout the universe, disguised as black holes, and yet their presence remains tantalizingly undetectable. The implications of this challenge are profound. If gravastars exist but are indistinguishable from black holes, then a significant fraction of the so-called black holes observed in the universe could actually be these exotic vacuum core objects. This uncertainty forces astrophysicists to consider alternative models for many cosmic phenomena, from the behavior of accretion disks to the origins of gamma-ray bursts, gravitational waves, and high-energy cosmic jets. It also raises the possibility that our understanding of extreme physics, particularly at the intersection of quantum mechanics and general relativity, may be incomplete, and that objects like gravastars could provide a bridge to new physics. In summary, gravastars are extraordinarily difficult to detect because they replicate nearly all the observable features of black holes. Their strong gravitational fields, accretion signatures, and gravitational lensing effects are nearly identical to black holes of similar mass. Even advanced tools like high-resolution imaging and gravitational wave detectors face extreme limitations in distinguishing between the two. The very features that make gravastars potentially so dangerous, immense stored energy and the capacity for unexpected release, also make them stealthy and nearly invisible to our instruments. In essence, the universe could be teeming with these hidden cosmic powerhouses, quietly lurking behind the guise of ordinary black holes, waiting for the slightest perturbation to reveal their terrifying potential. Gravitational waves offer one of the most promising, yet subtle, avenues for distinguishing gravastars from black holes. These ripples in spacetime, first directly detected in 2015 by LIGO, are produced when massive objects accelerate violently, particularly in binary mergers. Black hole mergers generate a very characteristic gravitational wave signal, and in spiral phase as the two objects orbit each other, a merger peak, and a final ringdown as the newly formed black hole settles into a stable configuration. The elegance and predictability of these signals come from the unique properties of black holes, particularly the presence of an event horizon and a singularity. Gravastars, however, introduce a twist into this gravitational wave narrative. Because a gravastar lacks a singularity and may not have a true event horizon, its response to a violent merger is different. The ultradense shell surrounding the vacuum core can oscillate in ways that a black hole cannot. These oscillations produce tiny, but theoretically detectable, echoes in the gravitational wave signal after the main merger event. Imagine striking a bell. The initial strike produces a loud sound, but subtle vibrations continue long after, gradually fading away. Similarly, a gravastar merger could produce secondary ringing effects, echoes of gravitational waves, that linger after the main signal. These echoes are absent in black hole mergers, where the event horizon absorbs disturbances almost immediately. The timing and amplitude of these echoes depend on the properties of the gravastar's shell and core. For instance, a thicker or denser shell would produce slightly different frequencies than a thinner, less massive shell. The vacuum core's energy density also plays a role, subtly altering how spacetime vibrates under stress. In principle, if scientists detect these echoes in future gravitational wave signals, they could serve as indirect evidence of gravastars existing in the cosmos. Detecting them would be revolutionary, not only confirming a new class of objects but also challenging our fundamental understanding of how matter and energy behave under extreme gravitational conditions. Detecting these echoes, however, is extraordinarily difficult. The signals are predicted to be weak, often buried in noise from detectors or background astrophysical events. Current gravitational wave observatories like LIGO and Virgo are incredibly sensitive, but teasing out the subtle differences between a standard black hole ringdown and a gravastar echo requires both improved instrumentation and sophisticated data analysis techniques. Some researchers have claimed tentative hints of echoes in past observations, but these results remain controversial, with alternative explanations often more plausible. Nonetheless, the search continues, as even a single confirmed detection would append decades of black hole research. The existence of gravitational wave echoes also raises exciting possibilities for probing quantum gravity. Black holes, according to classical general relativity, possess an event horizon where information is lost, a paradox that has puzzled physicists for decades. Gravastars, lacking a true event horizon, could allow information to escape in subtle ways, and the echoes in gravitational waves might carry signatures of these processes. In other words, each gravitational wave signal from a potential gravastar merger could be a treasure trove of information, revealing not just the nature of the object but also the behavior of spacetime under conditions where quantum and relativistic effects intersect. Furthermore, echoes could also provide insights into the stability of gravastars. The persistence, strength, and frequency of these echoes may reveal whether the object is in a stable equilibrium or teetering on the edge of collapse. A particularly strong or erratic echo pattern might indicate that the balance between the vacuum energy and the gravitational pull of the shell is fragile, hinting at the possibility of sudden energetic events, such as explosive releases of the stored vacuum energy. This makes gravitational wave observations not only a diagnostic tool but also a potential early warning system for understanding when a gravastar might behave unpredictably. Interestingly, the concept of echoes also introduces a potential observational test for exotic physics beyond general relativity. Black holes are well described by Einstein's equations, but gravastars invoke additional physics, such as vacuum energy cores and shell dynamics, that require modifications or extensions of classical theory. If echoes are confirmed, they would be direct evidence that our current understanding of gravity is incomplete, opening doors to new models that unify quantum mechanics and general relativity. It would signal that the universe is stranger than previously imagined, with objects that not only hide behind the veil of extreme gravity but actively store and manipulate energy in ways we are only beginning to their eyes. The hunt for gravitational wave echoes is thus a high-stakes, high-reward endeavor. It challenges astrophysicists to push the limits of detection technology, data analysis, and theoretical modeling. Every merger observed by LIGO, Virgo, and future detectors like LISA or the Einstein telescope could carry the fingerprints of gravastars, waiting to be decoded. If these faint signals are found and confirmed, the discovery would fundamentally alter our understanding of compact objects, revealing that some of the black holes we have been observing for decades might, in fact, be these exotic, potentially explosive gravastars. In short, gravitational wave echoes are more than a scientific curiosity. They are one of the few tangible ways we might detect an object that is otherwise almost indistinguishable from a black hole. They embody both the promise and the peril of gravastars. Promise in the form of new physics and understanding, peril in the sense that these objects, hiding silently behind the mask of black holes, could harbor energies capable of cosmic-scale disruption. The echoes are whispers from the universe's most extreme laboratories, offering clues about the true nature of space-time, matter, and energy under conditions far beyond anything on Earth. The absence of a singularity in a gravastar fundamentally changes the way we think about the extremes of space-time. In a black hole, matter collapses under gravity to an infinitely dense point known as the singularity. This creates a zone where the known laws of physics break down. General relativity predicts infinite curvature of spacetime, and quantum mechanics struggles to define what happens at such scales. Essentially, singularities are cosmic blind spots, regions where our current understanding completely fails. Gravastars, by contrast, eliminate this singularity, replacing it with a vacuum energy core that maintains a finite, albeit extreme, energy density. This shift opens up a landscape of strange, fascinating, and potentially unsettling physics. Without a singularity, space-time behaves very differently near the center of a gravastar. In a black hole, the singularity is a point of infinite curvature, which pulls all matter and light inexorably toward it. Time itself slows infinitely as one approaches the event horizon, freezing at the singularity from the perspective of a distant observer. With a gravastar, however, time and space near the vacuum core are warped but not infinitely so. The ultra-dense shell and outward push of vacuum energy create a delicate equilibrium that prevents infinite collapse. This means that, theoretically, time could continue to progress in ways that would be impossible inside a black hole. Matter approaching the gravastar would still experience extreme tidal forces, but it would not be crushed to an infinitesimal point. This absence of a singularity has profound implications for causality and the structure of spacetime itself. In a black hole, the singularity represents a point of no return not just physically, but conceptually. The laws of physics as we know them cannot describe what occurs there. In a gravastar, the absence of singularity preserves a finite, if extreme, spacetime structure, allowing for the possibility that information or energy could interact with or even escape from the interior under specific circumstances. This is particularly significant in the context of the black hole information paradox, which has challenged physicists for decades. Without a singularity, the destructive endpoint of matter and information is removed, opening the door to a universe where fundamental laws are preserved even under extreme gravitational conditions. Spatial geometry inside a gravastar is also intriguing. The vacuum energy core exerts an outward pressure that counteracts the inward pull of gravity, which effectively prevents the formation of an event horizon in the traditional sense. Space within this core is highly curved but stable, unlike the infinite curvature near a black hole singularity. Light traveling through or near the interior might follow bizarre, looping paths, bending in ways that challenge our classical intuition. From a relativistic perspective, these regions could act as space-time lenses or energy traps, bending trajectories of matter and radiation in ways that might create exotic observational signatures. Another implication concerns the behavior of matter and particles. In black holes, the singularity implies that any matter crossing the event horizon is inevitably crushed into infinite density. In a gravastar, matter approaching the shell might be compressed to extreme densities but never completely destroyed. The ultra-dense shell acts as a kind of pressure boundary, where quantum effects may dominate and exotic states of matter could exist, potentially including quark-gluon plasmas or other high-energy configurations. This means that, hypothetically, the physics near the core of a gravastar could allow for phenomena that are impossible inside a black hole, offering a unique laboratory for extreme matter and high-energy physics. Time dilation is affected as well. In a black hole, the closer you get to the event horizon, the slower time passes relative to an outside observer, ultimately freezing at the singularity. In a gravastar, the equilibrium between outward vacuum energy and inward gravity modifies this effect. While time dilation near the shell would still be extreme, it would not become infinite. This means that, unlike in a black hole, processes near the core could, in theory, continue and influence the outside universe, albeit indirectly. For example, oscillations of the shell or shifts in the vacuum energy could propagate outward, producing subtle gravitational or electromagnetic effects that might eventually be observable. Additionally, removing the singularity changes how entropy and thermodynamics operate. Black holes are known to have extraordinarily high entropy, proportional to the area of their event horizon, but the exact meaning of this entropy is tied to the mystery of the singularity. Gravastars, lacking a singularity, may have a different entropy structure, with thermodynamic properties dominated by the interplay between the shell and vacuum energy core. This could allow for the storage and release of vast amounts of energy without violating known physical laws, leading to extreme cosmic phenomena that are theoretically possible but physically impossible inside a traditional black hole. Quantum effects near the core would also be radically different. Black holes present a situation where quantum mechanics and general relativity collide at a singularity, producing unresolved paradoxes. Gravastars, by replacing the singularity with a finite vacuum core, allow for a regime where both quantum mechanics and relativity remain valid, albeit under extreme conditions. This opens up possibilities for exotic quantum states, unique particle interactions, or even new forms of radiation that could escape the shell under certain perturbations. From a conceptual standpoint, the absence of a singularity challenges our very understanding of cosmic extremes. Black holes have long been seen as the ultimate endpoints of massive stars and the most extreme gravitational objects in the universe. Gravastars, by avoiding singularities, suggest that the universe might have ways to achieve extreme densities and gravitational effects without crossing into zones where physics breaks down. This has profound implications not only for astrophysics but for cosmology, particle physics, and our broader understanding of the universe. In essence, the lack of a singularity means that gravastars occupy a middle ground between conventional massive objects and black holes. They allow for extreme curvature, massive gravitational pull, and high-energy phenomena, yet avoid the infinite densities that create paradoxes in theoretical physics. This makes them a uniquely fascinating object for studying the fundamental laws of nature, while also providing a potentially terrifying cosmic entity. An object capable of harboring immense energy and extreme gravitational effects, yet hidden behind a deceptively black hole-like facade. A gravastar, if it exists, would be a cosmic powerhouse, capable of influencing its surroundings in ways both subtle and catastrophic. Although it shares many outward characteristics with a black hole, such as extreme gravity and the ability to trap light, it possesses internal structures and energy dynamics that could make it even more unpredictable. For stars and planetary systems in its vicinity, a gravastar could be an existential threat, its effects ranging from the slow, inexorable tug of gravity to sudden bursts of energy with potentially devastating consequences. First, consider the gravitational influence. Like black holes, gravastars are extremely massive, often several times the mass of our Sun, or even millions of times greater if we're talking about supermassive candidates at galactic centers. This mass alone exerts a powerful gravitational pull that can destabilize orbits of nearby stars, planets, and other celestial bodies. However, unlike a black hole, a gravastar may have a fluctuating outer shell that can oscillate or shift under certain conditions. These oscillations could subtly alter the gravitational field in the surrounding space. Over thousands or millions of years, even minor variations could perturb stable orbits, causing stars to drift closer to the gravastar or be flung into highly elliptical or chaotic paths. Entire solar systems might be slowly nudged into instability, potentially leading to collisions, ejections of planets, or even the disruption of stellar life cycles. The vacuum energy core adds another layer of danger. The outward pressure of this core counteracts gravity inside the gravastar, maintaining its structural integrity. However, if the core's equilibrium is disturbed by external collisions, accretion of massive amounts of matter, or internal instabilities, the stored energy could be released in a dramatic fashion. Nearby stars could be bathed in intense bursts of radiation or high-energy particles, essentially frying planetary atmospheres or igniting new astrophysical phenomena. A single gravastar event could rival the energy output of supernovae, emitting a torrent of gamma rays, X-rays, or other exotic radiation capable of devastating nearby regions of space. Tidal forces represent another insidious risk. While gravastars may not possess a true singularity, their gravitational pull is still immensely strong near the surface of the ultradense shell. Stars passing too close would experience extreme tidal stretching, akin to the spaghettification near a black hole, though perhaps slightly mitigated by the absence of a singularity. Even if a star is not entirely torn apart, these tidal forces could strip away outer layers, creating massive stellar winds of plasma that interact with the gravastar's own magnetic or energetic fields. This process could destabilize the star itself or contribute to a chaotic accretion disk around the gravastar, generating unpredictable radiation and particle emissions. If the gravastar is a supermassive object at the center of a galaxy, like the one believed to reside in the Milky Way, the stakes are even higher. Its gravitational influence extends across thousands of light-years, affecting star clusters, interstellar gas clouds, and even the trajectories of entire galactic arms. Unlike a conventional black hole, a gravastar might periodically release bursts of vacuum energy, causing shockwaves through the surrounding galactic environment. These shockwaves could compress interstellar gas, triggering massive bursts of star formation, or conversely, they could strip gas away, halting stellar birth in affected regions. Such episodic behavior would make the galaxy's evolution less predictable than in a universe governed solely by standard black hole physics. Theoretical scenarios also suggest that gravastars could interact with binary or multiple star systems in particularly dramatic ways. Imagine a star orbiting a gravastar in a highly elliptical trajectory. If the gravastar's shell oscillates or releases energy, the orbiting star could be accelerated to extreme velocities, potentially being ejected from its system entirely. In more extreme cases, the gravastar's energy releases could induce stellar collisions or supernova-like events in nearby stars, propagating chaos through local star clusters. Unlike black holes, whose destructive effects are primarily limited to direct consumption or tidal shredding, gravastars introduce an additional, unpredictable layer of energetic disruption. Even planets far from the gravastar would not be entirely safe. High-energy radiation from the vacuum core, particularly gamma rays or cosmic rays generated by shell instabilities, could travel vast distances, impacting planetary atmospheres and potentially sterilizing surfaces. If a gravastar replaced a black hole in our galactic neighborhood, it could alter the radiation environment for solar systems hundreds or thousands of light-years away, increasing mutation rates, stripping atmospheres, or destabilizing planetary climates. In essence, the influence of a gravastar could extend far beyond its immediate gravitational grip, acting as a hidden cosmic hazard for nearby life-bearing worlds. Another layer of potential danger arises from accretion dynamics. If a gravastar captures gas, dust, or even stars from nearby systems, the interaction with its shell could generate intense bursts of energy that radiate outward. Unlike black holes, where infalling matter disappears behind the event horizon, a gravastar could convert some of the gravitational and vacuum energy into explosive or radiative phenomena before it is absorbed, producing sudden, unpredictable flares visible across interstellar distances. These energetic bursts could destabilize nearby systems in ways that black holes simply do not, introducing a level of unpredictability that makes gravastars uniquely threatening to their cosmic neighborhoods. Ultimately, the gravastar's combination of immense mass, vacuum energy dynamics, oscillating shells, and potential for sudden energy release makes it a more capricious cosmic predator than black holes alone. While black holes are deadly but predictable, pulling matter inexorably into a singularity, gravastars carry the added element of surprise. They may mimic black holes for decades or centuries, quietly influencing orbits and radiation environments, only to unleash bursts of energy with little warning. For nearby stars, this means that life cycles, planetary stability, and even the survival of stellar companions could be at the mercy of an object whose internal mechanisms remain purely theoretical. In a universe filled with supernovas, neutron stars, and black holes, gravastars, if real, would be the ultimate cosmic wildcard. Massive enough to dominate gravitationally, energetic enough to alter nearby systems, and unpredictable enough to make even seasoned astronomers uneasy. The invisible yet immense danger they pose is not only physical but also epistemological, challenging our ability to forecast cosmic events and predict the behavior of extreme astrophysical objects. Imagine, for a moment, that the gargantuan black hole we've come to accept as the heart of our galaxy, Sagittarius A*, is not a black hole at all, but a gravastar, a gravitational vacuum star harboring a vacuum energy core beneath an ultradense shell. The very thought reshapes not just our cosmic maps, but the way we understand our place in the Milky Way, and it casts a long shadow of existential unease over the future of life and technology in our solar system. Sagittarius A* sits approximately 26,000 light-years from Earth, a colossal gravitational anchor around which the stars of the galactic center orbit. Astronomers have inferred its mass, about 4 million times that of the Sun, based on the orbits of surrounding stars, particularly the famed S-stars whose rapid movement provides a kind of celestial dance revealing the invisible force at play. If this massive object were actually a gravastar rather than a black hole, its gravitational influence on the stars and interstellar matter around it might remain almost indistinguishable, but the internal mechanics, energy dynamics, and potential dangers would be radically different. First, consider what it would mean for time, matter, and radiation near the galactic center. Unlike a black hole, which imposes a true singularity and an absolute event horizon, a gravastar could permit subtle interactions between its interior and the surrounding space-time. This doesn't mean we could casually drop a probe inside and return it safely. The gravitational and energetic forces remain extreme, but it opens the tantalizing possibility that certain phenomena we currently attribute to black holes might behave differently. Matter spiraling towards Sagittarius A*, instead of being crushed irreversibly at a singularity, could interact with the vacuum energy core and the oscillating shell in ways that temporarily store or redirect energy, potentially producing bursts of high-energy radiation or exotic particle emissions. For the humans on Earth, the immediate effects would be negligible due to our distance. The Sun's orbit around the galactic center, and indeed the stability of our entire solar system, would remain largely unaffected under normal conditions. However, from a cosmic perspective, a gravastar at the galactic center introduces a layer of unpredictability that could manifest over millions of years. If the gravastar's shell were to become destabilized, or if the balance between vacuum energy and gravity shifted, bursts of gamma rays or high-energy particles could propagate outward across thousands of light-years. While this is not an immediate threat, it suggests that Earth, and indeed the entirety of the inner galaxy, could be subjected to radiation fluxes or energetic shockwaves that would have been impossible under the assumption of a classic black hole. The philosophical implications are equally profound. Black holes have long been a symbol of the ultimate cosmic dead end, a region where matter, energy, and information vanish into a singularity, never to be observed again. They serve as both literal and figurative boundaries in our understanding of physics. If Sagittarius A* is a gravastar, the central monster of our galaxy is no longer a simple cosmic endpoint. Instead, it becomes a kind of extreme but structured laboratory, a region of spacetime where physics stretches to its limits but does not break entirely. It represents a universe in which the most powerful gravitational objects might be less predictable than we imagined, capable of storing immense energy internally and releasing it in ways that could ripple through the galaxy unpredictably. For astronomers, this scenario transforms the way we interpret observations. The flares, jets, and occasional bursts of X-rays detected from the region around Sagittarius A** could be reinterpreted as phenomena originating from the gravastar's shell or core rather than from accretion processes near an event horizon. The orbits of S-stars, which have been used to confirm the black hole hypothesis, would remain largely consistent with the gravastar model, because the gravastar's mass distribution can mimic that of a black hole with remarkable fidelity. The challenge would lie in detecting subtle differences, perhaps gravitational wave echoes from internal shell oscillations, or minute deviations in the paths of stars or gas clouds near the core, that could finally tip the scales in favor of the gravastar hypothesis. From a societal standpoint, knowing that the galaxy's central black hole is actually a gravastar is both thrilling and terrifying. It would mean that a vast, hidden reservoir of energy exists just a short cosmic distance away, energy capable of influencing the Milky Way structure, triggering gamma-ray bursts, or sending gravitational ripples across the galaxy. While the likelihood of catastrophic interaction with Earth remains vanishingly small, the knowledge itself forces a reimagining of our place in the cosmos. Humanity has always viewed the black hole at the galactic center as a remote, untouchable object of awe. The gravastar, in contrast, is simultaneously awe-inspiring and slightly unnerving, because its potential behavior includes unpredictability and energetic instability that black holes, at least conceptually, do not. If Sagittarius A* is a gravastar, it also reshapes the narrative of galactic evolution. Black holes are understood as endpoints of massive stars, entities that slowly grow by accreting matter. Gravastars, however, could represent an alternate evolutionary path, one in which the collapse of a massive star is halted by the formation of a vacuum energy core rather than a singularity. This suggests that our galaxy might harbor more gravastars than we currently suspect, hidden among objects assumed to be black holes. Each of these objects could subtly shape the evolution of their surrounding stars and gas clouds in ways that diverge from standard black hole models. Finally, the human imagination is stirred by the psychological weight of such a discovery. Knowing that the central anchor of our galaxy is not just massive and gravitationally dominant but also potentially volatile, storing unfathomable amounts of energy, transforms our perspective of the cosmos from predictable and elegant to slightly chaotic and mysterious. It reinforces the idea that the universe is far stranger than our models suggest, and that some of the most dangerous and fascinating objects may be those we can barely detect, let alone fully understand. In this sense, a gravastar at the heart of the Milky Way is not merely a scientific curiosity. It is a cosmic riddle, a silent guardian of energy whose behavior could challenge the limits of astrophysics for centuries to come. Detecting a gravastar presents one of the most tantalizing and frustrating challenges in modern astrophysics. By their very nature, gravastars are designed to be nearly indistinguishable from black holes when viewed from afar. Their immense mass curves space-time in a way that mimics the gravitational signature of a black hole, and their dense shells prevent us from seeing directly into their vacuum energy cores. Despite these challenges, scientists have begun to consider subtle observational clues that could differentiate a gravastar from a black hole, turning the quest into a high-stakes cosmic detective story. One primary avenue for detection lies in studying the behavior of light and matter near what we currently identify as black holes. Because gravastars might lack a true event horizon, light falling toward a gravastar's surface could be temporarily trapped or redirected rather than swallowed irreversibly. In theory, this could produce a distinctive pattern of radiation or light echoes that would differ slightly from the absorption profile of a conventional black hole. Telescopes like the Event Horizon Telescope, which captured the first image of the shadow of a black hole in M87, could, in principle, detect such anomalies, though the differences would be extremely subtle and require incredibly precise measurements. Small variations in the shadow's shape or unexpected fluctuations in emitted radiation could hint at the presence of an ultra-dense shell rather than an event horizon. Gravitational waves offer another promising, albeit indirect, method of detection. When two massive objects merge, be they black holes, neutron stars, or potential gravastars, they send ripples through spacetime that can be detected by observatories like LIGO and Virgo. For black holes, these waves follow a fairly predictable pattern, an in-spiral, merger, and ring-down phase, all consistent with the presence of an event horizon and singularity. Gravastars, however, could produce subtle echoes in these gravitational waves after the initial merger. These echoes would arise because the gravastar's shell can reflect or modulate gravitational waves differently than a black hole's event horizon. Detecting these echoes requires not only extremely sensitive instruments but also a careful filtering of noise and precise modeling to distinguish real signals from statistical anomalies. Researchers have already begun searching for such echoes in past gravitational wave data, but as of now, no conclusive evidence has been found. Still, the possibility keeps theorists excited, because even a faint detection could revolutionize our understanding of extreme gravity. High-energy astrophysics provides yet another observational window. If gravastars periodically release energy from their vacuum energy cores, either through shell instabilities or sudden shifts in equilibrium, they could produce bursts of X-rays, gamma rays, or other high-energy radiation. These emissions might resemble those from black hole accretion disks, but with subtle differences in timing, spectrum, or intensity. Space telescopes like Chandra, XMM Newton, or FEMI could detect unusual flaring patterns or energy distributions that hint at a gravastar rather than a black hole. For instance, sudden, short-lived gamma-ray bursts in regions where we expect steady black hole accretion activity could point toward the presence of an energy-releasing gravastar. Orbital dynamics of nearby stars and gas clouds also offer potential clues. Just as astronomers inferred the existence of Sagittarius A** by tracking the orbits of the S-stars, they could look for anomalies that might suggest a gravastar rather than a traditional black hole. Even tiny deviations in orbital precession or velocity could, over time, accumulate into measurable discrepancies. These differences could arise from the fact that a gravastar's shell and core may interact subtly with surrounding matter, producing gravitational effects that are slightly out of line with classical black hole predictions. Long-term monitoring of stars near suspected black holes might eventually reveal these tiny deviations, providing indirect evidence of a gravastar's existence. Yet, despite all these theoretical detection methods, gravastars remain extraordinarily elusive. Their defining features are often designed to mimic black holes almost perfectly, which is why they were proposed in the first place, to resolve paradoxes like the black hole information problem while remaining consistent with observed gravitational phenomena. Even when energy releases or gravitational wave echoes occur, separating these signals from background astrophysical noise is a monumental challenge. Many observed phenomena could be explained by alternative mechanisms, from complex accretion physics to interactions with dark matter, making it difficult to claim a definitive detection. In addition, the distances involved pose a severe limitation. Most candidate black holes, including supermassive ones like Sagittarius A*, lie thousands or millions of light-years away. At these distances, even the most sophisticated telescopes struggle to resolve fine details, meaning that the internal structure of a gravastar, its vacuum energy core and ultra-dense shell, remains hidden behind layers of extreme gravitational lensing and high-energy emissions. Earth-based instruments, no matter how advanced, can only infer properties indirectly, increasing the uncertainty. Despite these challenges, the pursuit itself is a driving force in modern astrophysics. Searching for gravastars pushes the limits of observational technology, gravitational wave modeling, high-energy astrophysics, and theoretical physics. Every telescope upgrade, every new detector, and every refinement in computational modeling brings scientists closer to potentially identifying these objects, or at least placing constraints on their existence. The quest embodies a fascinating interplay between imagination and empirical rigor, demanding both bold theoretical speculation and painstaking observational discipline. Ultimately, detecting a gravastar is not just about confirming a hypothetical object, it's about testing the boundaries of our understanding of gravity, space-time, and the fundamental laws of the universe. If some of the black holes we've catalogued for decades turn out to be gravastars, it would force a rethinking of not only black hole physics but also the evolution of galaxies, the behavior of matter under extreme conditions, and the nature of cosmic energy itself. For humanity, it's a reminder that the universe is stranger and more complex than our current models suggest, and that even objects we think we understand might conceal hidden layers of reality. Even as the concept of gravastars captures the imagination of astrophysicists and the public alike, it is crucial to recognize that they remain firmly in the realm of theoretical speculation. Unlike black holes, whose existence has been confirmed through multiple independent lines of evidence, from stellar motions around invisible masses to direct imaging of their event horizons, gravastars have no direct observational proof. The idea is compelling, elegant in its theoretical construction, and potentially able to resolve some of the perplexing paradoxes of black hole physics, yet it is a hypothesis that has yet to cross the threshold into empirical certainty. Scientific skepticism is a foundational principle in the study of gravastars. The notion that a star could collapse into a vacuum energy core enveloped by an ultra-dense shell challenges conventional understanding of gravitational collapse. While physicists Powell Mazer and Emil Motola proposed gravastars as a solution to the black hole information paradox and other singularity-related problems, the astrophysical community requires more than theoretical appeal to accept them as real. Every prediction made about gravastars must eventually be testable through observation or experiment, a standard that has yet to be satisfied conclusively. There are several reasons for this caution. First, gravastars are designed to mimic black holes almost perfectly. Their gravitational influence on surrounding stars, the curvature of spacetime, and the way they bend light can be nearly indistinguishable from that of a true black hole. This makes observational differentiation extraordinarily difficult. Even the most sophisticated instruments, such as the Event Horizon Telescope or LIGO's gravitational wave detectors, can only hope to capture subtle deviations that might hint at the presence of a gravastar. Until such deviations are observed and confirmed beyond doubt, any claim of a gravastar's existence must remain speculative. Second, the internal structure of a gravastar, the vacuum energy core, the ultra-dense shell, and the surrounding spacetime, rests on assumptions about exotic forms of matter and energy that are not yet fully understood or confirmed. The physics of vacuum energy, dark energy, and ultra-dense matter under extreme gravitational conditions is still a developing field. While theoretical models show that a gravastar could exist in principle, the practical formation mechanisms, stability conditions, and longevity of such objects are far from empirically established. It is possible that, under real astrophysical conditions, gravastars might collapse, dissipate, or evolve in ways that invalidate current theoretical predictions. Another reason for skepticism arises from the challenges of alternative explanations. Many phenomena that could be interpreted as evidence for gravastars, such as unusual gravitational wave patterns, gamma-ray bursts, or unexpected radiation flares, also have plausible explanations within the existing black hole paradigm. Accretion disk dynamics, magnetic fields, interactions with surrounding interstellar matter, or previously unknown astrophysical processes could all produce similar effects without requiring the existence of gravastars. Disentangling these possibilities is an ongoing challenge, and until a unique, unmistakable signature of a gravastar is observed, the hypothesis remains unproven. Moreover, skepticism in science is not merely about doubting new ideas, it is about rigorously testing them against the evidence. Gravastars, for all their theoretical elegance, demand the development of precise, falsifiable predictions. This includes quantifiable differences in gravitational wave emissions, specific radiation signatures, or measurable deviations in orbital dynamics around compact objects. Only when such predictions are tested, and ideally, when observations align unequivocally with these predictions rather than with black hole models, can gravastars graduate from intriguing speculation to accepted astrophysical reality. This skepticism is also a reflection of the broader scientific process. The history of physics is filled with theories that were mathematically beautiful and conceptually alluring but failed under empirical scrutiny. From the idea of the luminiferous ether to early models of atomic structure, the scientific method requires that elegance alone cannot substitute for evidence. Gravastars must survive this rigorous process if they are to be acknowledged as genuine cosmic entities. Yet, it is precisely this uncertainty that makes gravastars fascinating and slightly unnerving. They represent the edge of our knowledge, the frontier where known physics meets speculation, and where the universe might be far stranger than our current observations suggest. Scientific skepticism does not diminish their allure, it sharpens it. Every telescope, detector, and simulation is a step toward potentially confirming or refuting their existence, and this journey drives progress in astrophysics, general relativity, and our understanding of extreme matter-energy interactions. In essence, gravastars are a reminder that science is an ongoing quest, not a repository of immutable facts. They challenge scientists to look beyond conventional assumptions about black holes, singularities, and cosmic collapse. While they remain unproven, the hypothesis stimulates questions about the fundamental nature of spacetime, the behavior of vacuum energy, and the fate of collapsing stars. The skepticism surrounding them is not a limitation. It is a necessary safeguard, ensuring that when, if ever, a gravastar is observed, the discovery is robust, reliable, and transformative for our understanding of the cosmos. The true terror of gravastars does not come solely from their immense gravitational pull, their ability to trap light, or the unfathomable energies stored within their vacuum cores. Instead, the fear emerges from the profound uncertainty surrounding them, the possibility that the universe may be harboring objects that look exactly like black holes but behave in ways that defy all our expectations. Unlike black holes, whose properties, although extreme, are relatively well understood within Einstein's framework of general relativity, gravastars occupy a gray zone of physics, blending familiar gravitational effects with exotic, largely speculative quantum phenomena. This ambiguity transforms a gravastar from a mere astrophysical curiosity into one of the most unnerving hypothetical objects in the cosmos. Consider the scenario from a human perspective. Astronomers have spent decades cataloging black holes, modeling their interactions with surrounding matter, and predicting the behavior of stars orbiting these dark giants. The assumption has always been that these cosmic monsters follow the well-defined rules of general relativity. If, however, some of these black holes are actually gravastars, all prior predictions could be subtly, or drastically, wrong. The idea that a seemingly understood black hole could suddenly reveal new, unpredictable behavior is what makes gravastars particularly frightening. They are not merely unknown, they are potentially unknowable until we develop entirely new methods of observation or reinterpret existing data through a fundamentally different lens of physics. One source of unease comes from the energy stored in a gravastar's vacuum core. Unlike a black hole, which sequesters mass and energy irretrievably behind its event horizon, a gravastar could theoretically harbor immense quantities of dark energy-like material capable of exerting outward pressure. Should the delicate balance between the inward pull of gravity and the outward push of this vacuum energy be disrupted, the consequences could be catastrophic. A sudden shift could release enormous amounts of energy, producing gamma-ray bursts or other high-energy phenomena on a scale that could dwarf anything we have observed in typical black hole interactions. Unlike black holes, whose behavior is largely predictable, matter falls in, radiation is emitted from the accretion disk, and the singularity remains hidden. The potential for a gravastar to misbehave introduces an element of cosmic unpredictability that is deeply unsettling. Moreover, the absence of a true event horizon in a gravastar means that what seems trapped might not remain trapped forever. Light, matter, or radiation approaching a gravastar could be temporarily held in extreme gravitational tension, only to escape later in unexpected ways. This false imprisonment of matter and energy creates the possibility of delayed or sudden emissions that would appear inexplicable if interpreted under the assumption of a traditional black hole. For astronomers and astrophysicists relying on established models, such anomalies could seem chaotic or even threatening, undermining the predictability that underpins our understanding of high-energy cosmic phenomena. The psychological component of their terror is also significant. Black holes, though intimidating, are conceptually straightforward. They destroy everything that crosses their event horizon and warp spacetime in extreme ways. Gravastars, by contrast, challenge the very notion of what a black hole is. They exist at the intersection of known and unknown physics, simultaneously obeying and violating expected rules. The realization that the universe might be populated with objects that perfectly mimic black holes, yet operate under a fundamentally different set of physical laws, introduces a form of existential unease. It suggests that our current understanding of gravity, spacetime, and cosmic energy may be incomplete, and that the apparent order of the cosmos could be an illusion masking far stranger dynamics. From a practical perspective, this uncertainty could have real consequences for our models of galactic evolution and high-energy astrophysics. Supermassive gravastars at the centers of galaxies could subtly influence star formation, accretion rates, or orbital dynamics in ways that standard black hole physics does not predict. If one were to exist in close proximity to our solar system, the potential for unexpected energy release or gravitational anomalies, while low, would be far greater than if we were dealing with a classical black hole. Even without direct catastrophic effects, the mere possibility that the cosmic giants we've relied upon as predictable anchors might behave unpredictably is enough to inspire awe and fear. In essence, gravastars are terrifying precisely because they embody uncertainty on a cosmic scale. They blend the familiar with the unknown, masquerade as something we understand, and yet harbor the potential for behavior that could defy every expectation. Their existence would mean that the universe is more deceptive and more complex than previously imagined. Unlike black holes, whose extremes are terrifying but constrained within a framework we can calculate, gravastars invite a level of unpredictability that extends to the very foundations of physics: matter, energy, space-time, and even time itself. Ultimately, the fear of gravastars is philosophical as much as it is scientific. They confront us with the possibility that much of the universe might be hiding in plain sight, presenting itself in ways that seem familiar while masking its true nature. The universe may be populated with monsters that are indistinguishable from the ones we thought we knew, but whose behavior, energy, and influence could rewrite our cosmic assumptions in an instant. In this sense, the gravastar is not just a terrifying hypothetical object. It is a symbol of the universe's capacity for mystery, unpredictability, and unanticipated extremes. When it comes to cosmic threats, the universe seems to specialize in extremes, producing phenomena that dwarf human comprehension and challenge our sense of safety and scale. Supernovas, magnetars, and black holes already dominate this roster, each terrifying in its own right. Supernovas, for instance, are the explosive deaths of massive stars, releasing in seconds more energy than our Sun will emit over its entire 10 billion-year lifetime. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's, capable of wiping out entire atmospheres or disrupting electronics across vast distances. Black holes, of course, are the ultimate predators, regions of spacetime where gravity becomes so intense that not even light can escape, hosting singularities where the laws of physics as we know them collapse. Yet, if gravastars exist, they may rise above these cosmic threats, not through sheer visibility or immediate danger, but through the insidious combination of power, mystery, and unpredictability. Supernovas are spectacular but relatively well understood. Their life cycle is predictable, and while the explosion is cataclysmic, the timeline and mechanisms are documented extensively. We can model the fusion processes leading to core collapse, the shockwave propagation, and the distribution of heavy elements into the interstellar medium. Their threat to life is considerable only on the cosmic scale. A supernova would need to be within tens of light-years to directly affect Earth. Magnetars, while more exotic than supernovas in terms of their magnetic effects, are similarly understood in terms of the mechanics of neutron stars and magnetic field evolution. Their danger is localized, extreme, and spectacular: high-energy gamma rays and magnetic flux that can sterilize or destabilize nearby regions, but largely confined by their rarity and distance. Black holes are inherently terrifying due to their absolute nature. Their singularities are points of infinite density where our current physics breaks down entirely, and their event horizons act as cosmic one-way doors. Anything that crosses this threshold is lost forever. Black holes also distort time and space to extreme degrees, producing gravitational lensing that can warp entire galaxies' appearances. Yet, their behavior is, at least theoretically, predictable. We can calculate orbital motions, accretion disk dynamics, Hawking radiation predictions, and even model their mergers to generate gravitational waves. The known dangers of black holes, though immense, are framed within a set of mathematical laws that provide a measure of predictability. Gravastars, however, may surpass all three in a more subtle, insidious way. Unlike supernovas, their effects might be long-term and cumulative rather than instantaneous. Unlike magnetars, their power is hidden, not broadcasted through radiation and magnetic fields. And unlike black holes, they might mimic the most terrifying features of these objects while avoiding the strict constraints of predictability. A gravastar could appear to be a black hole, bending light, trapping matter, and generating gravitational waves, yet harbor a fundamentally different internal structure. The energy stored in their vacuum cores could, in principle, rival or exceed that of the most massive stars or black holes, and the potential for sudden release makes them uniquely threatening. The danger hierarchy, then, becomes more nuanced. Supernovas are immediate and explosive threats, but their predictability and distance mitigate the sense of cosmic uncertainty. Magnetars are dangerous and exotic, but their rarity and localized effects provide a framework for understanding their risk. Black holes are the ultimate point of no return in terms of matter and information, terrifying in their inevitability. Gravastars, in contrast, combine aspects of all these threats. They have the gravitational power and apparent invisibility of black holes, the potential for sudden energetic outbursts akin to supernovas or magnetars, and the unsettling unpredictability of an unknown physical structure. In terms of cosmic fear, the uncertainty alone, an object indistinguishable from a black hole but potentially capable of defying known laws, places gravastars at the top of the hierarchy of terror. Furthermore, gravastars introduce a level of indirect danger that other cosmic monsters do not. While supernovas and magnetars threaten through direct emissions of energy, and black holes through gravitational inevitability, gravastars might influence the universe in subtle, insidious ways. Their long-term effects on nearby stars, accretion of matter, and potential gravitational instabilities could ripple across galaxies without immediate detection. The sheer unknowability of how a gravastar might evolve, erupt, or interact with its environment over millions or billions of years introduces a type of cosmic horror that is qualitatively different from the dramatic explosions or violent magnetic pulses of other threats. In this sense, gravastars are not just another cosmic hazard, they are a meta-threat. They embody the fear of the unknown compounded with the fear of familiar dangers disguised under a false identity. A gravastar could quietly masquerade as a benign black hole for eons, only to reveal catastrophic behavior when conditions change, like an enormous, ticking energy bomb hidden behind a veil of normalcy. For astrophysicists, this raises both professional excitement and existential trepidation. The potential for discovery is immense, but the realization that we might have misidentified a cosmic powerhouse for decades, or longer, is humbling and unnerving. So when ranking cosmic monsters, gravastars occupy a terrifyingly unique position. They are not necessarily the most immediately destructive, nor the most conspicuous, but they are potentially the most unpredictable, the most elusive, and the most capable of rewriting our understanding of cosmic dangers. They are a shadowy apex predator in the hierarchy of universal threats, combining the worst features of black holes, supernovas, and magnetars while remaining cloaked in uncertainty. In a universe where extreme phenomena already challenge comprehension, gravastars offer a reminder that the most dangerous entities may be those we cannot yet confirm, measure, or fully understand. Their true menace lies in their potential to exist unnoticed, to operate beyond current physical expectations, and to suddenly reveal energy or behaviors that could ripple across space-time in unforeseen ways. Gravastars do more than just challenge our understanding of astrophysics. They confront the very foundations of how we perceive reality, space, and time. At a glance, they might appear simply as an alternative to black holes, a technical tweak in theoretical physics. But if we dig deeper, their implications ripple across philosophy, cosmology, and the conceptual limits of human knowledge. To imagine a gravastar is to confront a universe that is stranger, more subtle, and more unpredictable than we've been trained to accept, a universe in which the rules we rely upon may be provisional, approximate, or incomplete. From a philosophical standpoint, gravastars force us to question the nature of certainty in science. Black holes, for all their dramatic extremity, provide a framework of predictability. Their singularities, while mathematically perplexing, are clearly defined within general relativity. Their event horizons, while absolute, are calculable and observable in principle. Gravastars, by contrast, occupy a liminal space between the known and the unknowable. They appear, at first glance, to be black holes. Yet their internal structure might violate or circumvent fundamental laws we assume are universal. This duality, being something familiar on the outside while radically alien on the inside, challenges the basic scientific assumption that appearances reliably reflect reality. It introduces a layer of epistemological uncertainty. What if much of the universe is populated by objects that look like one thing but behave like something else entirely? What if our maps of space-time are not simply incomplete, but systematically misleading in ways we cannot yet detect? In terms of space, gravastars compel us to rethink the geometry of the cosmos. Black holes warp space to an extreme, producing a singularity where curvature becomes infinite. Gravastars, however, might avoid singularities entirely, replacing them with a vacuum energy core. The absence of a singularity changes the nature of space-time around these objects. Time might behave differently near a gravastar's core. Causality could be affected in subtle ways, and the familiar predictions of orbital dynamics or photon paths could deviate from expectations. If gravastars exist, the very notion of spacetime as a smooth, continuous fabric governed by general relativity may need refinement. It implies that space might host hidden pockets of exotic physics, regions where energy, gravity, and geometry interact in ways that challenge classical intuition. Time, too, becomes an unstable concept in the presence of gravastars. Near a black hole, time dilation is extreme but calculable. Clocks slow predictably as they approach the event horizon. A gravastar, with its vacuum core and potentially non-traditional boundary conditions, might warp time in ways that defy simple extrapolation. Could a photon orbit a gravastar for decades before escaping? Could matter temporarily suspended near its surface experience time differently from a distant observer in ways that exceed even the predictions near a black hole? These questions extend beyond physics into the realm of philosophy, forcing us to confront the idea that time may not be uniform, continuous, or absolute in the universe's most extreme corners. Gravastars also challenge our metaphysical understanding of reality itself. Much of modern cosmology rests on the principle that physical laws are universal. A gravastar suggests a loophole in that principle. Here is an object that behaves like a black hole but is governed by fundamentally different internal physics. The implication is profound. The universe might be far more heterogeneous than our current models assume. There may exist domains of matter, energy, and space-time where conventional rules break down, or where they are replaced by rules we do not yet comprehend. Philosophically, this is destabilizing because it undermines the assumption that science is merely a process of observation and deduction. If the cosmos contains objects whose external behavior masks radically different internal rules, then prediction, observation, and even the concept of objective knowledge become more tenuous. The gravastar also invites reflection on human perception and cognition. We tend to interpret the universe through familiar categories: stars, planets, black holes, and so forth. Gravastars defy categorization, blending features of known objects with the radical unknown. They remind us that the universe is not obligated to conform to our mental frameworks. What appears predictable may conceal chaos. What seems familiar may hide novelty. In a philosophical sense, gravastars are a mirror of human epistemic humility, illustrating the limitations of perception, measurement, and even imagination when confronted with the extremes of existence. Furthermore, gravastars provoke existential reflection. If these objects exist, they demonstrate that the universe can harbor immense power, danger, and complexity in forms that evade detection. Our cosmic neighborhood may be more dangerous, more mysterious, and less knowable than previously assumed. In a universe where a seemingly ordinary black hole might secretly be a gravastar, we are reminded of the fragility of certainty, the limits of human understanding, and the vastness of phenomena that lie beyond direct perception. This has profound implications not just for science, but for philosophy, influencing how we think about reality, knowledge, and our place in a cosmos that is at once comprehensible and inscrutable. Ultimately, gravastars push us to reconsider fundamental concepts. They challenge our notions of space as merely curved geometry, of time as linear and uniform, and of reality as objectively knowable. They demonstrate that the universe may contain layers of structure and behavior that are invisible to us, operating in parallel with the familiar cosmic order. Philosophically, this is both exhilarating and terrifying. It expands our imagination while humbling our assumptions, revealing that the most profound mysteries may not be distant or abstract, but woven into the very fabric of what we thought we understood. Whether gravastars exist in reality or remain purely theoretical, their study occupies a fascinating and essential frontier in modern physics, pushing the boundaries of what we understand about gravity, quantum mechanics, and the fundamental structure of the universe. Einstein's general theory of relativity has been the backbone of modern cosmology, explaining gravity as the curvature of spacetime caused by mass and energy. It has passed countless observational tests, from the bending of light around massive objects to the recent detection of gravitational waves. Yet, even as successful as it is, general relativity is incomplete. It struggles to reconcile with quantum mechanics, the other pillar of modern physics. Singularities, like those found in black holes, expose this incompleteness. They are points where densities become infinite, spacetime curvature diverges, and Einstein's equations break down entirely. Gravastars, in this sense, are not merely theoretical oddities. They are conceptual tools for probing the limits of current physical laws. Exploring gravastars challenges physicists to think beyond traditional models. Unlike black holes, gravastars replace the singularity with a vacuum energy core, suggesting a new way that gravity and quantum effects could coexist in extreme conditions. This hypothetical structure encourages scientists to ask, can the extreme warping of spacetime coexist with exotic forms of energy without collapsing into infinite density? Can quantum effects stabilize objects that would otherwise form singularities? Answering these questions requires merging insights from general relativity, quantum field theory, and even speculative concepts like dark energy and exotic matter. In doing so, gravastar research propels physics into a frontier where conventional assumptions are tested, refined, or even discarded in favor of new paradigms. Another critical frontier is the investigation of gravitational waves. The detection of ripples in spacetime from black hole and neutron star mergers has already revolutionized astrophysics. Gravastars offer a potential twist in this narrative. If they exist, they could produce subtle echoes in gravitational wave signals that differ from traditional black hole mergers. Detecting these echoes would not only provide evidence for gravastars but also offer a direct window into extreme physics beyond Einstein's framework. It forces theorists to refine models of compact objects, spacetime curvature, and energy distribution in ways that conventional black hole physics does not require. The effort to differentiate gravastars from black holes, then, drives innovation in both observational techniques and theoretical models, stretching our ability to measure, predict, and interpret the cosmos. Studying gravastars also engages one of the most perplexing puzzles in theoretical physics, the information paradox. Black holes pose a fundamental dilemma. Information about matter falling into a black hole appears to be lost forever, violating the principle of quantum mechanics that information must be conserved. Gravastars, with their non-singular structure, offer a potential resolution. If information can be stored or reflected in ways that avoid destruction, we gain insight not just into exotic stars, but into the very reconciliation of gravity with quantum laws. The consequences are profound. Understanding gravastars could illuminate the principles governing the flow of information in the universe, potentially guiding a new synthesis between general relativity and quantum theory, sometimes referred to as quantum gravity. Even the concept of dark energy gains relevance through gravastar studies. The core of a gravastar is theorized to be a vacuum energy region, reminiscent of dark energy, the mysterious force accelerating the expansion of the universe. By examining how a gravastar could remain stable under extreme gravitational pressure while maintaining a vacuum energy core, physicists explore practical manifestations of energy that are otherwise only inferred on cosmological scales. This opens a door to understanding how exotic energy interacts with spacetime, a question that could have ramifications for cosmology, particle physics, and the search for a unified theory. Moreover, gravastars exemplify the iterative nature of science at the frontier. Even if no gravastar is ever observed, the theoretical exploration itself generates value. Models must be tested, predictions refined, and observational strategies devised, all of which advance our understanding of extreme physics. The tools developed, whether in gravitational wave detection, high-resolution astrophysical imaging, or computational simulations, benefit other areas of research. Each step toward verifying or falsifying the gravastar hypothesis teaches us more about the universe's limits, even if the objects themselves turn out to be purely hypothetical. In that sense, gravastars are a crucible for scientific progress, blending imagination, rigorous mathematics, and observational ingenuity. Finally, the study of gravastars encourages cross-disciplinary collaboration. Astrophysicists, theoretical physicists, cosmologists, and computational scientists must all engage in a dialogue to explore these objects. The work demands not only knowledge of general relativity and quantum theory but also creativity in applying new mathematics, interpreting gravitational data, and considering exotic forms of matter and energy. Gravastars, therefore, are more than an object of curiosity. They are a catalyst for advancing the entire field of physics. They push the community to question assumptions, test extremes, and pursue answers that may eventually lead to a theory of everything, or at the very least, a more complete understanding of how the universe behaves under conditions far beyond our terrestrial experience. In essence, gravastars represent a frontier where the known meets the unknown, where Einstein's elegant but incomplete framework meets the messy complexity of quantum realities and exotic energy. Whether they exist or not, they embody the spirit of scientific exploration. Curiosity coupled with rigorous analysis, speculation balanced with observation, and the relentless pursuit of knowledge in realms where certainty is fleeting. They are a symbol of the ongoing expansion of human understanding, a reminder that physics is not static, and that the universe may always hold phenomena that challenge the very foundations of what we believe to be true. As we come to the close of this exploration into gravastars, it's impossible not to feel a shiver of cosmic awe, and maybe even fear. The universe has always been a place of mystery, filled with phenomena that defy human intuition. From supernovae that outshine entire galaxies, to magnetars with magnetic fields billions of times stronger than anything on Earth, to black holes that swallow light itself. But gravastars occupy a uniquely unsettling space in this pantheon of cosmic monsters. Unlike the blazing certainty of a supernova or the observable power of a magnetar, gravastars are shadows, concealed, theoretical, and profoundly enigmatic. They may already be lurking where we expect black holes to be, quietly bending space-time, trapping light, and storing unimaginable energy, all while eluding detection. The beauty and terror of gravastars lie in their very unknowability. A black hole is terrifying because we can describe its effects: spaghettification, event horizons, singularities. But a gravastar is frightening in a different, subtler way. It could mimic those known horrors while harboring surprises we cannot yet predict. Its vacuum energy core might store and release colossal amounts of energy without warning. Its lack of a singularity could allow for strange, counterintuitive behaviors of time and space, and its outer shell might hold the line between stability and catastrophic explosion. In other words, the gravastar's danger is wrapped in uncertainty. It is a cosmic object that refuses to fit neatly into our current understanding, challenging every assumption about extreme physics. This uncertainty strikes at the core of human curiosity and our need for comprehension. We like the universe to be predictable, to map its dangers, and to label its forces. Yet gravastars defy this. They occupy the liminal space between reality and theory, between what is observable and what is imaginable. The scariest things in the universe may not be the objects whose power we can measure, but those whose existence we can only infer, whose behavior we cannot fully anticipate. It is the tension between appearance and hidden truth, the gap between theory and observation, that elevates the gravastar from a mere astrophysical curiosity to a profoundly unsettling idea. Imagine standing at the edge of the Milky Way, looking towards Sagittarius A*, the supermassive black hole at our galaxy's center. Now imagine discovering that this gravitational anchor is not a black hole at all, but a gravastar, a nearly perfect imitation hiding physics we cannot yet grasp. Suddenly, the familiar cosmos feels less secure. The stars we chart, the orbits we predict, the cosmic events we assume we understand, all rest on a foundation that might be more fragile and strange than we realized. The gravastar embodies the ultimate cosmic unknown, a reminder that nature's most profound secrets may be hidden in plain sight, masked by familiarity yet concealing forces beyond comprehension. Philosophically, this forces reflection not only on the universe but on ourselves. If we cannot fully understand the most extreme objects in existence, how can we claim mastery over nature in general? Gravastars, even as theoretical constructs, teach humility. They remind us that knowledge is provisional, that certainty is rare, and that the universe may harbor phenomena forever beyond the reach of direct observation. They are the embodiment of a principle as old as philosophy itself, that the unknown is both terrifying and beautiful, both humbling and inspiring. From a scientific perspective, the pursuit of understanding gravastars represents the cutting edge of human inquiry. Researchers push the limits of theory, observation, and technology, striving to detect subtle gravitational wave echoes, to model exotic vacuum energy cores, to distinguish these enigmatic objects from the black holes we thought we knew. Every experiment, every simulation, every telescope observation is a step into the unknown, a dance along the boundary between what we can prove and what we can only imagine. The pursuit itself is a journey through the frontier of knowledge, a reminder that the universe is vast, strange, and often more terrifying than fiction. And perhaps that is the ultimate lesson of the gravastar. It is a symbol of the universe's unrelenting mystery. Its theoretical existence challenges physics, philosophy, and imagination alike. It confronts us with the possibility that the scariest objects in the cosmos are not those whose effects we can measure, but those whose presence we can only hypothesize, whose behaviors defy prediction, and whose true nature remains veiled. In the grand theater of the cosmos, gravastars are the ultimate hidden actors, moving silently behind a mask, waiting for the moment when their secrets might be revealed, or when their reality might remain forever out of reach. So, as we step back from the equations, the simulations, and the speculative models, we are left with a haunting, exhilarating thought. The scariest things in the universe might be the ones we can't even prove exist, yet. Gravastars may be real, or they may remain forever theoretical, but their mere possibility stretches our imagination, challenges our understanding, and reminds us that the cosmos is far stranger, more complex, and infinitely more mysterious than we can ever fully grasp. And in that uncertainty lies both the terror and the wonder of existence itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.